Alrighty, folks. So, welcome to lesson 2 of chapter 9, the second lesson of Physics 30. In this lesson, we're going to be extending on our talk here on momentum. So, in the first lesson, we introduced the idea of momentum as well as the idea of impulse, which was a change in momentum. We're going to extend that today in this lesson to look at conservation of momentum, the fact that momentum is conserved, and how that can allow us to analyze multiple objects interacting, right? So, in the previous lesson, we talked about the momentum of a car as it moved or of one object as it moved, right? Now we're going to actually look at multiple objects when they interact with each other. Maybe they bounce off of each other, or maybe one object blows up into two different objects, right? Momentum is a tool that can allow us to figure out if it started in a certain way, how will it play out, how will it end up because of this conservation law. So before we get into the law of conservation of momentum, we kind of need to do a quick recap of systems, isolated versus non-isolated systems. Okay, that's often the case when we're talking about conservation laws because we might say something is conserved within a system. Okay, so what is a system? It's not too fancy. Okay, a system is really just the part of the universe that we're interested in at the moment, right? We kind of define what our system is. So it might be a ball flying through the air, two cars as they collide, the earth and the moon. It's whatever you're interested in, right? Typically when we're analyzing a system, we're trying to, the interaction that we're interested in, we'll call that the system. So if it's two cars colliding, our system might be those two cars, right? If we're bouncing a ball off the ground, it might be the ball and the ground, okay? But that's all a system is. It's the part of the universe that we're analyzing at the moment, okay? So an isolated system is a system on which no external forces act to do work. Remember, work means change in energy, right? So if a force is acting to change an object's energy, then we say that that object is not an isolated system. There's an external force acting on it, changing its energy, right? It is adding energy into the system or possibly removing energy from the system, right? So if you think about like if your system is a ball and you roll the ball along the ground, right? We can tell that that's not an isolated system. The ball is not an isolated system because eventually the ball will come to a stop, right? And that's because friction, in that case, friction between the ball and the ground, it's not part of our system. That's an external force to our system because we said the ball was just our system. And so that external force is doing work on the ball to remove energy and eventually bring it to a stop, right? And we know in an isolated system, no energy can enter or leave the system. So energy is leaving our ball there because of the action of this external force. Now, if we expand our system a bit, if we say, okay, but what if we include the ground and the ball and even the surrounding air? That would get closer to actually being an isolated system now. Because yes, the ball is losing energy, but a lot of that energy is going out as heat into the air or into the ground, right? Friction is converting that ball's kinetic energy into thermal energy. Okay, so again, system is just the part we're interested in. So if we say our system here is just the ball, it's not an isolated system, definitely not. Friction is an external force doing work to remove energy from the system, right? And changing the ball's kinetic energy. And as we'll see, also changing the ball's momentum, right? But if we expand our definition of our system here, if we say, well, let's include the ground in the system and the air in the system, that's closer to isolated, right? Yes, energy is being, moved from one place to another, so to speak, but it's still kind of staying in our system if we expand the definition of our system, okay? So an isolated system, again, it's just a system on which no external forces act to do work, act to change the energy of the system. So there are no net forces from outside of the system doing work on it. Remember, work is a change in energy, and therefore no energy is added or removed from the system by some external forces, okay? No forces from outside of the system are changing the motion of any objects within the system. That's what an isolated system is, right? It's just kind of left to be, it's doing its own thing, and nothing from outside of what we're defining as the system is causing the motion of the objects within that system to change, okay? So external forces might act on a system and we could still consider it isolated, but they must be balanced so that there are no net external forces. Because we know from physics 20 that a force can act on an object and its motion not change as long as that force is canceled out by something else. So to return to the ball example, right? What if this surface was frictionless, right? Now, of course, no true frictionless surfaces exist, but if this surface were actually frictionless, the ball actually would be on its own an isolated system, right? You might say, but there's a force of gravity acting downwards on the ball. And that's true, but there's also a normal force acting upwards on the ball, so those two cancel each other out, and there's therefore no net external force, right? There might be forces acting on it, but they cancel each other out. So there's no net external force acting on the ball, and what will the ball do? It will keep rolling forever, the same velocity, same energy. No external force is acting to do work, to actually change the ball's energy in this case. So that ball rolling on a frictionless surface, that would be an isolated system. No energy is entering, no energy is leaving. The motion of the ball is not changing due to the action of some external force, okay? So just a quick reminder, isolated, no matter, no energy is allowed to enter or leave the system. A closed system, no matter is allowed to enter or leave, but energy can enter or leave. And then an open system, energy and matter can just come and go as they please, right? So like for an example of an open system, picture, an open mug of coffee. We know energy can leave because the thermal energy leaves the coffee and it gets cooler, right? We also know matter can leave because if you look at a hot cup of coffee, you see steam coming off of it, right? That's water, that's matter, that's water vapor leaving the surface of the coffee, okay? Exiting the cup, exiting our system. A closed system might be like a thermos, right? A thermos, no matter is allowed to leave. If you've tightly sealed up your thermos, the water can't leave. The steam from the coffee's not leaving. But we know eventually the thermos will get cold, so clearly energy can still leave the system, right? And in an isolated system, neither matter nor energy is allowed to enter or leave, right? So that might be like a hypothetical perfect thermos that truly keeps your coffee the same temperature, and it doesn't allow energy to leave at all, right? So truth be told, in the real world, systems are almost never truly isolated, right? There's no such thing as a perfect thermos. The laws of thermodynamics tell us that eventually the thermal energy will leave the coffee, right? And it will get cool. So the energy almost always will eventually dissipate. The only truly isolated system is the whole universe itself, right? No energy enters or leaves the universe itself. That being said, we can approximate many systems as isolated, okay? Especially with what we're going to deal with a lot in these collision interactions is very short time scales. So like, for example, two cars might collide, right? And then we know eventually both of those cars are going to come to a stop, right? Like they'll hit each other, maybe they'll skid for a bit, but they'll eventually come to a stop, right? And so, yes, obviously that system's not isolated because friction between the ground and the cars brought them to a stop. But that being said, if we analyze in the moments just before the collision and just after the collision, that friction has not had enough time to actually cause an impulse and change the object's momentum, change their motion. Remember, impulse takes a force being applied for a certain amount of time. So this is one way we can approximate an isolated system, is that over short enough time scales, like in the instant just before the collision and the instant just after the collision, it is pretty close to no energy, no momentum having left the system, having been removed from the system by that external force. Friction in the example of the two cars colliding that I just used, okay? But just keep in mind, again, isolated system, an external force no external force acts to do work on it, and therefore no external force removes energy from it, and therefore, as we'll see, no external force can change the motion, and therefore change the total momentum of the system. All right, now with that behind us, let's move into actually talking here about conservation of momentum. So we've been talking about how energy is something that is conserved, right? We know that energy can't be created or destroyed. And so in an isolated system, that means if there's no way for energy to exit or enter the system, then the total amount of energy in that system will stay the same, right? It is conserved. Momentum is actually also a quantity that is conserved in an isolated system. Now, you don't have to take my word for that. We're going to prove using stuff that we already know that momentum kind of has to always be conserved in an isolated system, okay? But before we do that, let's just talk about what it means for a quantity to be conserved. By the way, new physics principle alert. This is one of the major physics principles. This is one of those fundamental ideas, one of the rules of the universe, okay, that is a law that we never see broken. It's the law of conservation of momentum. We have never observed momentum to not be conserved, okay? So if we take a look on the back of our formula sheet, this is physics principle number 4. Again, these numbers are just given by Alberta Education because they like to ask stuff on the diploma like, okay, you answered this question, but do you know what physics you were applying to do it, right? And then they say, so which physics principle number did you use? They're just referring to the number given on the back of your formula sheet. So if we do a conservation of momentum calculation and they ask us what did we use, we would say we used physics principle number 4, the law of conservation of momentum. So what does it actually mean for something to be conserved, right? What does it mean that momentum is always conserved? Well, we know that conservation means it is not created or destroyed. It can move from one place to another. It can be transferred, but it can't just disappear, and it also can't just appear. It can't be created. So for something to be conserved, it means that it's never created nor destroyed, right? The total amount stays constant. However much you start with, you end up with. So that's the key idea. The total initial amount of that quantity will be equal to the total final amount of that quantity. So this is what makes conservation laws so powerful for physics analysis, right? Because that means if you know how much of a quantity there is at the beginning, you know it's going to be the same total at the end, right? If you know the total momentum of the two cars before they collide, you know their total final momentum will be the same. And so that means you can work out how certain cars might be moving after the collision, right? Momentum is used to analyze collisions, especially, and this is what makes momentum, well, one of the things that makes momentum especially powerful is that it works even when we can't use conservation of energy. Because we know, I mean, in Physics 20, we saw this a lot too, right? Often, it's not that conservation of energy is broken, but it's that energy is really good at leaving systems in ways that we can't analyze. We don't have equations to, right? The big one being heat. When two cars collide, a lot of heat is given off. So it's not that that energy is destroyed, but it's converted into a form that leaves the system into the atmosphere, and we really don't have a good equation or a good way of knowing how much heat left the system. So often conservation of energy, while especially powerful, it can fail us in situations where energy leaves the system. Momentum is easier to keep track of, so to speak. So this is where conservation of momentum comes in really handy, is when we can't actually make use of the law of conservation of energy. Again, not because it's broken, just because the energy leaves the system in a form that we don't have a calculation to keep track of it with. Okay, so the system losing mechanical energy usually has heat, sound, etc. So like I said, at the end of this lesson, with the law of conservation of momentum, we'll be able to determine maybe how drivers in a collision were driving before the collision based upon the motion of the cars after the collision, simply using the law of conservation of momentum. Because if we know their momentum after the collision, well, we know they must have had the same total momentum before the collision, thanks to the law of conservation of momentum. Momentum is never created nor destroyed. The total initial amount will be the same as the total final amount. And again, that is why conserved quantities, anything that's conserved, it's great for physics analysis, because all we need to know is the total initial value, and we can be sure that the total final value is the same. Now, it may change forms, or it may be transferred to other objects, okay? But its total amount does not change. So the momentum of an object within a system might change, right? Maybe one car's momentum changes, but the other car's momentum will change in such a way to keep the total the same, right? Just like we saw with conservation of energy. You drop your calculator, right? It is losing gravitational potential energy, but at the same time, it's gaining kinetic energy so that the total energy in the system stays the same. Very similar here for momentum. One object's momentum might change, but another object's will change in such a way so as to keep the total the same. And so what's even better about law of conservation of momentum, it's an especially powerful tool in our kit, and that's because, don't forget, momentum is a vector, meaning that it's conserved in both magnitude and direction. We can't say, oh, the amount of momentum stayed the same, but the direction changed. Well, no, then momentum wasn't conserved because momentum is a vector, right? Direction matters. The same momentum in a different direction isn't actually the same momentum. Direction is important to momentum, okay? And so think about that. That's really helpful because now we're going to be able to say not only how much momentum there will be afterwards if we know the momentum before, but also in which direction, right? So that's pretty exciting. Okay, now I'm sure you can't wait to dive in and start using this law of conservation of momentum. But before we do, let's just take a second to prove that the law of conservation of momentum actually makes a ton of sense and it's unavoidable. And all we need is stuff you already know to prove that that's the case. All right. So again, conservation of momentum calculations, like any conservation calculation, they often involve, initial and final. They're useful in situations where the initial conditions kind of predetermine what the final conditions can be, right? And so for these, they usually involve the interaction of two or more objects. A car collides with a truck, a firecracker explodes into 4 pieces, a bullet is fired out of a gun, those types of things, right? Now, in all of the above interactions, the two objects exert an equal in magnitude but opposite in direction force on each other. That's just Newton's third law. So that's why I said, based on stuff you already know, we'll see how the law of conservation of momentum becomes unavoidable. There's no way momentum couldn't be conserved when two objects interact. Quick reminder of Newton's third law. Remember, that says whenever two objects interact, they exert equal but opposite forces on each other. Sometimes said as for every action, there's an equal and opposite reaction, right? And again, you can feel Newton's third law for yourself right now. Push down on the table and you will feel the table pushing up on you just as hard, right? To jump upwards, you push the ground downwards so that the ground pushes back up on you. So when these two balls hit each other, they're going to be in contact with each other, exerting forces on each other, equal in size, but opposite in direction. And so that force is present for as long as the two objects are interacting, right? As long as they're touching, they're exerting that force. As soon as they stop touching, they're no longer exerting that force on each other, right? Rest your hand on the table, you can feel it pushing back up on you. Lift your hand up off of the table and you no longer feel it pushing on you, of course, right? They exert that force while they're in contact with each other, on each other. Okay, now, remember from lesson 1 that a force acting on an object for a given time period results in the object experiencing an impulse, a change in its momentum, right? A change in momentum, an impulse, will be equal to some force acting on it times the amount of time that that force acted on it. And remember, this really actually just came from Newton's second law. We said that forces equal to mass times acceleration, but acceleration is just change in velocity over change in time, and rearranging that, multiplying both sides by time, we get that a force times a time is equal to mass times change in velocity. So this is just, right, mass times velocity final minus mass times velocity initial. That's just the change in momentum, right? And so is this, the impulse. Okay. Now, we're going to look at this situation. I just want to show you a visual of it happening so you can kind of picture what's going on here. So we're just going to let these two balls collide with each other. Okay, I'm going to play it full speed first, and then we'll go step by step, just so you can kind of see, right? Blue ball comes in, hits the pink ball, they bounce off of each other. Let's watch that happen again, and let's think now about the forces involved, okay, and Newton's third law, and what that means for each object. So I'm going to press play, let them get close, and then we'll go frame by frame here. Okay, ready? So the blue ball's coming in, pink ball's coming to the left. They are now in, oops, I missed it. They're now in contact with each other, right? So what does Newton's third law tells us? Tells us that they're exerting equal but opposite forces on each other. So can you see how, again, if we just let this play, right? The pink ball, restart. The blue ball is coming into the right, and it's going to hit the pink ball, and while they're in contact with each other, the blue ball is pushing the pink ball to the right, right? Meanwhile, the pink ball is pushing the blue ball to the left. When objects interact, they exert equal but opposite forces on each other. And we can see that the result of those forces is that both objects' velocity changes, right? Because the blue ball pushed the pink ball to the right, the pink ball got accelerated to the right. So now it's actually moving to the right in that case, right? And vice versa, because the pink ball pushed the blue ball to the left, the ball is now moving to the left, okay? So that force caused changes in their motion and therefore changes in their momentum. Now let's think about the force and how long it's acting on each ball, because we know the forces are equal but opposite, right? And they're also acting for the same amount of time, right? Because how could it be different amounts of time? The force is there while the balls are in contact. So as long as they're in contact, blue is pushing pink to the right, and pink is pushing blue to the left, right? So as soon as they break contact, they're no longer exerting those forces. And they stop breaking contact at the same time, of course, right? How could one be in contact with the other, but the other is not in contact with the other, right? How could blue be in contact with pink, but pink's not in contact with blue? So they exert equal forces on each other for the same amount of time, but in opposite directions. Well, if we look at this equation here, we can already kind of see the beginnings of the law of conservation of momentum showing up, right? They exerted the same size force, but in opposite directions, for the same amount of time. So their change in momentum has to be the same number, but in opposite directions. So think about that. The pink ball's momentum did change by the same amount as the blue ball, but they did it in opposite directions. So overall, what was the change in momentum of the system, right? Maybe one changed by positive 1 kilogram meter per second, while the other changed by negative 1 kilogram meters per second. So what's the overall change in momentum of the system? 0 kilogram meters per second. In other words, the momentum total did not change. Sound like the law of conservation of momentum? Okay, let's dive into this a little bit more. So let's think about, this is the same situation, but now written out in our notes here, okay? We're going to think about Newton's third law as it relates to interactions like the examples above. We're going to imagine that the two balls ram into each other in a head-on-head collision, right? So the black ball is moving to the right, the white ball is moving to the left. Now, while they are colliding, while they're in contact with each other, Newton's third law tells us that the balls will exert equal but opposite forces on each other, right? So while they're in contact, the white ball is pushing the black ball to the left, the black ball is pushing the white ball to the right. As soon as they break contact, that force goes away. So they are exerting that equal force on each other for equal amounts of time, just in opposite directions. So starting with Newton's third law, the law of conservation of momentum also becomes apparent. Let's start with Newton's third law, which just says that the force, I'll use black and white here, we could just say 1 on 2, but actually no, let's do 1 on 2. So the force of object 1 on object 2 will be equal but opposite to the force of object 2 on object 1. Okay, so now to start thinking about impulses and momentums here, what I'm going to do, since we know the time they're in contact is obviously the same for each ball, right? They're in contact with each other. Let's just multiply both sides by that change in time. We're allowed to do that. It's the same number. So object 2 will be feeling this force for this amount of time, and object 1 will be feeling this force for this amount of time. They're the same forces, just in opposite directions. All right, well now what does this represent? This is the impulse of object 2, right? This is the force that was acting on it for this amount of time. So this is the impulse of object 2. And that's equal but opposite to the impulse experienced by object 1. Okay, now like we said, this is actually already very close to telling us the law of conservation of momentum. If we interpret this correctly, this really is the law of conservation of momentum, right? However, object 2's momentum changes will be equal but opposite to how object 1's momentum changes. So that overall, those changes in momentum actually cancel each other out and give us no change in momentum. In other words, momentum is conserved. Okay, let's take this a little step further though. I'm going to bring everything to one side, so I'm going to add this over. And here we go, really starting to look like the law of conservation of momentum now. Because look, we're saying that the change in this object's momentum plus the change in this object's momentum is 0. In other words, the total change in momentum is 0. Okay? Now, what is the change in momentum of object 2? Well, a change in anything is final minus initial, right? So what we're really saying here is momentum 2 final minus momentum 2 initial. That's just the change in object 2's momentum plus the change in object 1's momentum. So plus the change in object 1's momentum, right? Momentum 1 final minus momentum 1 initial. That's just the change in object 1's momentum. So that's all I've done so far, okay? Break these down into final minus initial. Now, if we rearrange this a little bit, we can really see how the total initial momentum must equal the total final momentum. So what we've got right now, let's just, simplify this out a bit. We don't need those brackets anymore. So momentum 2 final minus the momentum of object 2 initial plus the momentum of object 1 final minus the momentum of object 1 initial needs to equal 0. And now if we just bring the initials all to one side and the finals all to one side, we'll see this. So I'm going to add momentum 1 initial and momentum 2 initial to both sides. And look what that's going to leave me with. Momentum 2 final plus momentum 1 final equals momentum 2 initial plus momentum 1 initial. So see what we're saying here, right? Just if I rewrite this a little bit, the initial momentum of object 1 plus the initial momentum of object 2 will be equal to the final momentum of object 1 plus the final momentum of object 2. Right? This is the law of conservation of momentum. Just came from Newton's third law and what we know about impulse, right? This is saying, what is this? What is this left side? This is the total initial momentum in the system. We had 2 objects, so 2 momentums to think about. Add up their momentum initially. That's the total momentum in the system initially. Afterwards, we still have 2 objects, so add up their momentum. That's the total momentum final. And we've showed here that all of the momentum initially has to be equal to all of the momentum finally, right? The law of conservation of momentum. Like I said, it's unavoidable just based on stuff we already knew. Newton's third law, right? And a little bit of stuff we talked about in the previous lesson, that a force acting for a time causes an impulse, which is really just Newton's second law. So we've derived this law of conservation of momentum by just applying Newton's second and third laws. Cool, right? And so here it is, the law of conservation of momentum. The net, the total momentum, magnitude, and direction, right, of all objects in an isolated system before any interaction will be the same as the net momentum, magnitude, and direction of all objects after the interaction. So if you add up all the momentum before, including direction and signs, right, it will be the same number as adding them all up after. Okay, so mathematically, how we would say that, this just means, this is the Greek letter sigma, it just means total, okay? Add all of the momentums up initially, so the total initial momentum will equal the total final momentum. That's the law of conservation of energy. That is physics principle number 4. And that's where we're going to start for almost all calculations from here on out, okay? Again, I find when students struggle more with this stuff is they try to jump straight to some big equation, or they're trying to see where it's ending. I'm a physics teacher. I don't jump straight to some big equation. I start with the basics. That's how physics, that's the nice thing about physics, is you actually take some very simple starting points. The total momentum initial will equal the total final momentum. Okay, that's where we're going to start. And then we break it down and we get more specific to our problem. But whenever doing a conservation of momentum calculation, this should be our starting point. And then we can think about, okay, so how many objects are there? How many do I need to add up initially? How many objects are there afterwards? How many do I need to add up? Then we can break it down and focus on what we know, what we don't know, and what we can find, okay? But this is where we are going to start. If you're ever asking a question like, what formula do I use? If it's a conservation of momentum calculation, the answer is always going to be that, right? Total momentum initial equals total momentum final will be our starting point for 99% of these types of problems and analyzing these situations. Okay, so we'll jump into that in a bit more in the notes here in a second, but first let's just pause and get a feeling for this law of conservation of momentum, okay? What's it actually look like? What's it mean? So I've got an animation here, a simulation where we can choose the numbers. By the way, these simulations are always posted in the agenda as well, so you can always go take a look and mess around with them yourself. I do encourage you to do that. It's a good way to get a feeling for this stuff, okay? But what I've got here, right now time is paused, but we have a red cart. You'll notice there the mass of the red cart is 1 kilogram, and its velocity right now is to the right 5 meters per second. So we're calling that positive 5. The blue cart, same idea, mass of 1 kilogram, but a velocity to the left. So we're calling its velocity negative 5 meters per second. Okay, so I want you to think about the momentum of the red cart. What would that be? We know that momentum equals mass times velocity, right? P equals mv. So its mass is 1 kilogram, its velocity is 5 meters per second. So the red cart's momentum is 5 kilogram meters per second to the right, right? It's 5 kilogram meters per second positive, if we're calling right positive. For the blue cart, it's 1 kilogram times negative 5 meters per second. So it has negative 5 kilogram meters per second of momentum, or 5 kilogram meters per second of momentum to the left. So what is the total momentum in our two-cart system right now? The red has positive 5 kilogram meters per second. The blue has negative 5 kilogram meters per second. So 5 plus negative 5 is 0. So the total momentum in this system right now is actually 0. Yes, individually the two objects have momentum, but the total momentum in the system is 0. Okay, let's let them collide and see what happens. Aha! Now look, the red cart bounced to the left, and its velocity is now negative 5 meters per second. So since its mass is still 1 kilogram, its momentum is now negative 5 kilogram meters per second. The blue cart is now positive 5 kilogram meters per second. So negative 5 plus 5 is 0. The total initial still equals the total final. Now notice, individually, yes, the cart's momenta changed, right? The red cart's momentum absolutely changed. The blue cart's momentum absolutely changed, okay? But the red cart on its own is not an isolated system, right? If we just call our system the red cart, well, then the blue cart is an external force acting to do work on it and change its momentum. But if we zoom out a bit and we define our system to be the two carts that are interacting with each other, then the total momentum was conserved. The red cart's momentum might have changed and the blue cart's momentum might have changed, but they both changed in opposite ways so as to keep the total momentum in the system constant. Total momentum was conserved here. Cool, right? All right, so similar experiment here now, but notice I've changed the red cart's initial velocity to positive 10 instead of positive 5. So that means the red cart's initial velocity, or initial momentum, is going to be mass times velocity, so 10 kilogram meters per second. Whereas the blue carts I've kept the same at negative 5 kilogram meters per second. So the total momentum in the system is going to be positive 10 plus negative 5 to give us positive 5 kilogram meters per second of momentum in our system right now. So there is net momentum. They don't cancel each other out perfectly. Right now, this system has a net momentum of positive 5 kilogram meters per second to the right. Let's see how that plays out. Here we go. Whoa, okay. So again, both cars' momentum changed. Did the total change though? Red now has 1 kilogram times negative 5 meters per second, or negative 5 kilogram meters per second of momentum. Blue now has positive 10 times 1, or positive 10 kilogram meters per second of momentum. So add those up, positive 10 kilogram meters per second plus negative 5. Hey, total final is also positive 5 kilogram meters per second, right? Total initial equals total final. Individually, their momenta changed, but the total momentum in the system did not. All right, let's run it another way here. So now look, I've changed the mass of the red cart. We know that could change its momentum. And I've adjusted the velocities a bit here, honestly, just to make the numbers work out nicely and not be decimals. But look, okay, so the momentum of our red cart is going to be 3 kilograms times 6 meters per second, or positive 18 kilogram meters per second. Our blue cart, I kept the mass at 1 kilogram. Now the velocity is at -2. So the blue cart has an initial momentum of -2 kilogram meters per second, right? 1 times -2. So what's the total momentum? Positive 18 from the red, -2 from the blue. So 18 plus -2 is positive 16 kilogram meters per second. That's the total momentum in our two-cart system to start with. The law of conservation of momentum tells us that the total final momentum after they collide must also be positive 16. Let's see what happens. Boom. Okay, so I'm going to pause there. Look, they hit each other. They bounced off. Okay, we'll just watch it one more time. Boing. Now the red cart has 2 meters per second in the positive direction. That's its velocity. So what's its momentum? Well, 3 times 2 is 6 kilogram meters per second. The blue cart has 1 kilogram times 10 meters per second, so 10 kilogram meters per second. So 6 kilogram meters per second from the red plus 10 kilogram meters per second from the blue is 16 kilogram meters per second. That's what we started with, right? 16, 16. Positive six, the total momentum in this system was 16 kilogram meters per second to the right to begin with, and it is 16 kilogram meters per second to the right to finish with, right? Transferred between the two objects, but the total momentum in the system stayed constant. Can you see how powerful this tool is to start thinking about, all right, if we know the conditions before and we know the conditions, or at least some of the conditions after, we can work out any unknown conditions, right? Conservation laws are incredibly useful for that reason. All right, now you might be saying that's great and they bounce off of each other and the numbers can work out, sure, that they come to give us the same total momentum. But like in a lot of real life collisions, things stick together, right? They don't perfectly bounce off of each other. So let's see what happens there. Does the law of conservation of momentum hold? So I've changed it to now an inelastic collision. You can see on the bottom there. We'll talk about what that means in a moment here, okay? But same starting situation here as the first trial we did before. The red cart has a initial momentum of positive 5 kilogram meters per second because it has a mass of 1 and a velocity of 5 meters per second. And the blue has a momentum of negative 5 kilogram meters per second. So what's the total momentum in the system right now? 0, right? 5 plus -5. What will the total final momentum be in the system? Without even thinking about it, we can say 0, right? It has to be the same, the law of conservation of momentum. Let's see how that looks if the carts stick together. Make a prediction. How will that look? 0 momentum, but the two carts stick together. Oh, they both just come to a stop, right? By sticking together, they kind of become one object almost. So our two objects have become one object, right? And so if initially the total momentum of the system, the two objects together, was 0, then afterwards, when they're stuck together as one object, the total momentum can't change. It still has to be 0. And so our one object that we've created just won't be moving, right? But momentum was conserved. 0 net momentum to begin with, 0 net momentum to finish with, okay? Let's do another trial here. I'm going to keep it so that they stick together, okay? But now notice I've made it so that the net momentum in the system to begin with is not zero because I've given the red one more momentum to the right than the blue one has to the left. So notice the initial velocity of the red is positive 10 meters per second. So the red one has an initial momentum of 10 kilogram meters per second to the right. The blue one still has an initial momentum of 5 kilogram meters per second to the left. So add those up. We've got 10 plus negative 5 gives us a total initial momentum of positive 5, right? 10 plus negative 5. So there are positive 5 kilogram meters per second of momentum in our system initially. Let's see what happens finally. But we know there are going to be positive 5 kilogram meters per second total of momentum. Let's just see how it looks though. Aha, let's see that one more time. So, boom, they stick together. Both of their momenta change. Is the total still positive 5? Well, what's the total mass here? We've got 2 kilograms worth of mass now, right? The red and the blue cart together, they're each 1 kilogram. And that 2 kilograms of mass is moving at positive 2.5 meters per second. Positive 2.5 times 2 kilograms of mass gives us positive 5 kilogram meters per second of momentum. So initially, there was 5 kilogram meters per second of momentum to the right. Finally, there is 5 kilogram meters per second of momentum to the right, right? Total initial equals total final. Cool. All right, so let's just look at one final type of scenario here for conservation of momentum. You'll see on the bottom right, I've changed it now to explosion, meaning that, an explosion in physics means that they start together and then they blow apart, right? They break apart. So you can see now there, right? We've got the red cart and the blue cart. They're both sitting still, but they've got that little, bomb in between them that's going to explode and shoot them both in opposite directions. Now, what's the initial momentum in this system? Well, they're not moving, right? Nothing's moving, so the initial momentum is 0 plus 0 or 0, right? So without even thinking about it, what is the final total momentum in the system? It's 0, right? The law of conservation of momentum tells us the total initial will be the same as the total final. So if total initial is 0, total final better be 0. Now, that doesn't mean the red cart's final has to be 0 or the blue cart's final has to be 0. It means the total final has to be 0. So here we go. Let's let this bomb explode. And look at that, right? Red cart now has negative 10 kilogram meters per second of momentum. Blue cart has positive 10 kilogram meters per second of momentum. Add those up, 10 plus negative 10. The total net momentum in the system, final, is still 0. No momentum was created, no momentum was destroyed. The law of conservation of momentum. Now, one final trial here, okay, and then we'll go back to the notes. But look, now I've given these two carts that are stuck together, I've given them an initial velocity. So it's one object stuck together, but it's actually moving to the right. So there is momentum in the system initially, and then they're going to blow up and split apart. So what is the initial momentum in the system? Well, we've got, 2 kilograms of mass, the red and the blue cart put together, and it's moving, that 2 kilogram mass is moving at 2 meters per second to the right. So 2 times 2 is 4 kilogram meters per second of momentum to the right. Without even thinking about it, what's going to be the final momentum in the system, the final total momentum? It'll be the same thing. It'll be 4 kilogram meters per second. Individually, the two objects will have different momenta, but their sum will still be positive 4. Let's see how that looks. Aha! So look at this. Red cart now has 1 kilogram times negative 8 meters per second, or negative 8 kilogram meters per second of momentum. Blue cart now has 1 kilogram times 12 meters per second, or positive 12 kilogram meters per second of momentum. So 12 kilogram meters per second of momentum plus negative 8 gives us positive 4 kilogram meters per second of momentum. Total momentum was conserved, right? In both magnitude, same size, right? 4, and direction, positive to the right. Cool. Okay, and that's the law of conservation of momentum. That's what all there really is to it. The total initial momentum will equal the total final momentum. So let's start to analyze this in a bit more depth here now. All right, so as we saw there, right, yes, momentum is conserved, the total momentum stays constant, but it can also be helpful to think, right, of it being transferred from one object to another in interactions, right? As we saw, again, an individual object within the system might see its momentum change, right? We saw the red cart and the blue cart's momentum change individually, but the total, overall, the system's total momentum will not change. To kind of wrap our head around this, let's think about, just an example. A car traveling east and rear-ending a stationary truck. So I drew a little before and after diagram. Before and after diagrams are always very helpful when dealing with these conservation laws because they let you think about what's going on before and what's going on after. And we know that the total momentum will be the same here as the total momentum here. Okay, so before, the car is moving to the east, right? And the truck is not moving at all. So the total momentum in this system will definitely be to the east. We don't have any numbers, so we can't say what it is. But if we knew the car's mass and the car's velocity, we could say that, the total momentum would just be the car's mass times the car's velocity. The truck doesn't have any momentum right now because it's not moving before, okay? Now, afterwards, the truck is going to be moving to the east, right? The car hits it and pushes it to the east. The car, what's going to happen to the car? It's going to get slower, right? Because of this collision it's had with the truck. So the car gets slowed down, the truck gets sped up. Now, that means the car is going to end up with a little bit less momentum. I'll call that PC for car. If we do a vector addition diagram here, so we add now, because now the truck does have some momentum as well, right? To the east, because the car has pushed it to the east. So the car lost a little bit of momentum to the east, but the truck gained a little bit of momentum to the east. So that total, the momentum, if I draw my net momentum vector, which is from the tail of the first to the tip of the last, right? To draw a resultant vector, we always go from where we started to when we finished. The total momentum final is the same as the total momentum initial, right? The law of conservation of momentum. So see what I mean about transferring? It's kind of like the car has transferred some of its eastward momentum to the truck, right? The car lost some eastward momentum, but total momentum was still conserved because the truck gained some eastward momentum that it did not have before. So breaking that down here, what happens to the car's momentum? Well, it's decreased in magnitude, right? It now has less eastward momentum than it did before the collision, right? Because again, smashing into the truck, it gets slowed down. It still might be moving to the east, but it's slower. So momentum is mass times velocity. A slower eastward velocity gives a smaller eastward momentum. Okay, now what's the direction of the car's impulse in this situation? It had an eastward momentum and it lost some of that eastward momentum. That means it experienced a westward impulse, right? The change in momentum was to the west. Now that doesn't mean it's moving to the west, don't forget. It just means the change was such that it took away eastward momentum, right? And we call that a westward impulse. If we say east is positive, its impulse was negative. The change was negative, okay? So what happens to the truck's momentum? Well, it has increased in magnitude, right? It now has more eastward momentum than it did before. Before it wasn't moving at all. The cars come along and pushed it to the right, or to the east, I guess, right? So it's gained some momentum to the east. Notice the parallels here, right? This one lost some momentum. This one gained some momentum to the east, right? That's keeping the total momentum constant. What one lost, the other gained. So the total momentum in the car-truck system has stayed constant. And what impulse has it experienced? It's experienced an eastward impulse, right? To go from no momentum to having an eastward momentum, your momentum has changed to the east. You've gained eastward momentum. So what about the total momentum? Well, no change, right? I mean, just based on the law of conservation of momentum, we know that has to be true, right? No change. And we can see the reasons why when we examine this, right? Did the car's momentum change? Sure. Did the truck's momentum change? Sure. But in such ways that they cancel each other out to keep the total constant. Whatever the car lost in eastward momentum, the truck gained in eastward momentum. So the two impulses cancel each other out, right? Giving us a total change in momentum of 0. Equal but opposite changes in momentum for a total change of 0, right? In other words, the total initial momentum equals the total final momentum. The law of conservation of momentum, physics principle number 4 on your formula sheet. Okay, so now don't forget, momentum is a vector. Will the total initial momentum be the same as the total final momentum in magnitude, but also in direction? If the total initial momentum is 100 kilogram meters per second to the east, the total final momentum will be 100 kilogram meters per second to the east, right? If it's 100 kilogram meters per second to the north, momentum wasn't conserved. Momentum's a vector, right? It needs to be in the same direction to be the same thing. Okay, now this gets us thinking here as well, right? Can multiple objects that are all moving have a net momentum of 0? So every individual object is moving, so it must have momentum, right? P equals mv. So if v isn't 0, neither is p, the momentum. But altogether, can they have a net momentum of 0? Multiple objects that are all moving. Well, yes, they can. We've seen that actually happen already, right? Here are two objects, both moving, but their total momentum is 0 because they're same size but in opposite directions, right? Positive 5 kilogram meters per second for the red, negative 5 kilogram meters per second for the blue. So, yes, two objects with the same, that are both moving can have a total momentum of 0 because momentum's a vector. And remember, for vectors, they can cancel each other out. The same magnitude in the opposite direction can cancel one out. So, yes, as long as their momenta add to 0, right? To cancel each other out. So totally. Now, can they have a total kinetic energy of 0? Multiple objects that are moving. Energy, is that a scalar or a vector? Energy is a scalar, right? Energy doesn't have a direction. A car driving 100 kilometers per hour east and a car driving 100 kilometers per hour west with the same mass, they have identical kinetic energies because the v in 1/2 mv squared is speed. It doesn't give consideration to direction. Direction doesn't matter, right? I mean, we can kind of tell energy is a scalar. If you run down the stairs or you run up the stairs, that doesn't make a difference to the amount of energy, right? I mean, you can't run downstairs, be kind of tired, and then run back up the stairs and undo that energy cost, right? So no, there is no way for them to have 0 kinetic energy. There's no such thing as negative kinetic energy is one way to look at it, right? Kinetic energy to the east is positive. Kinetic energy to the west is positive because assigning a sign to them doesn't make any sense anyway, right? Direction has no consideration, no importance to scalars like kinetic energy. They really do just add up more and more and more. The more the objects are moving, the more kinetic energy you have. There's no such thing as canceling it out because it's in the opposite direction, because energy doesn't have a direction in the first place. Okay, so let's just talk about the different types of collisions and interactions. We saw them actually in that animation there. We did a quick tour of them, but let's formally define them, okay? So conservation of momentum applies to elastic collisions, inelastic collisions, and explosions. Those are the 3 types of interactions that we'll mainly look at, and pretty much all interactions fit into one of those categories, okay? So an elastic collision are those in which kinetic energy is also conserved. Note, kinetic energy is also conserved. You might be saying, but energy is always conserved, and you are correct. Total energy is always conserved. If it's an elastic collision, it actually means the kinetic energy was conserved. Okay, so total energy is always conserved, but we know that sometimes that kinetic energy can become heat and lost out of the system, right? If it's an elastic collision, we actually keep all the kinetic energy in the system. So no energy is converted to other forms such as heat, sound, or sometimes deforming the materials involved, right? If a car gets kind of banged up and crunched up after a collision, that took energy, so some of that kinetic energy that was in the car's motion has been lost to deforming the materials, okay? Now, a collision only has a chance at being elastic if the objects do not stick together, right? Now, be careful. That does not guarantee that it will be elastic. It's just the only possible scenario where it even could be elastic, right? Because they have to bounce off each other and then they're both still moving. They both still have a mass and a speed. So it's still possible for the kinetic energy to be conserved. Again, it won't always be, okay? Just because they bounce off of each other doesn't guarantee that it will be an elastic collision. But if they don't bounce off of each other, there's no way it could be an elastic collision. Which makes sense when we think about it. We move to the next one here. If an elastic collision is one in which kinetic energy is conserved, you can probably reason that an inelastic collision is one in which kinetic energy is not conserved. Okay, now again, sometimes I say that and students go, wait, I thought energy was always conserved. Total energy is still conserved. That's a law of physics. Energy cannot be created or destroyed. But it doesn't say that kinetic energy has to be conserved, right? We know kinetic energy can get converted into other forms. And so in an inelastic collision, that's what happens. Kinetic energy leaves our system and it goes into forms that we might not be able to calculate or keep track of, right? So some of the initial kinetic energy is lost as it is converted into other forms like heat, sound, or into, crunching up the materials that make the objects that are colliding, right? If the objects stick together, the collision must be inelastic. Because, think about it. The mass that's actually moving doesn't change when they stick together, but its speed does, right? So if kinetic energy is just 1/2 mass times speed squared, right? The two objects, their mass hasn't changed, but their speed has definitely changed, right? They've gotten slower typically, like we saw in the animation there, right? Two cars are moving, they stick together, now they're both moving slower. Well, their speed has decreased, but there's been no change in their mass, so it's impossible for the total kinetic energy of the system to not have changed. So here it is. This is what an elastic collision is. Sometimes students get bogged down in trying to memorize it, but it really is. It's just in an elastic collision. How do you check if something is elastic? You take the total initial kinetic energy, add up mv squared over 2 for every object involved, and see if it's the same as the total kinetic energy after the collision. If so, it was an elastic collision. If not, it was an inelastic collision, right? That's really all there is to it. We know how to calculate kinetic energy. So if we do it for every object before and every object after and we get the same number, there you go. That was an elastic collision. If not, there you go. It was an inelastic collision. Okay. Now an explosion, okay, it's just when one object splits up into two or more objects. Okay. Take a second and think about this. Would it be possible, you imagine you have a little bomb and it's going to blow up into two pieces that are flying away from each other. Let's say like that. Okay. Is it possible for kinetic energy to be conserved? What's the kinetic energy here? Is it moving? No, right? So the kinetic energy would be 0. Afterwards, is there kinetic energy? Well, yeah, there's a whole lot, right? This has a lot of kinetic energy. This has a lot of kinetic energy. They're moving in opposite directions, but remember, that doesn't matter for energy, right? These just add together to give us more kinetic energy because energy is a scalar. Momentum is still conserved, we know, because momentum is a vector. This much momentum to the left, this much momentum to the right. So the total momentum stayed the same, okay? But here, you're right, there's no way for kinetic energy to be conserved. We had no kinetic energy before. Now we have a lot of kinetic energy, right? Kinetic energy to the left, kinetic energy to the right, there's no such thing, right? It's just kinetic energy, okay? So it is clearly impossible for kinetic energy to be conserved in an explosion. Again, I can't stress enough, that doesn't mean energy is not being conserved, right? It's just kinetic energy is not conserved. What's actually happened here is that, chemical potential energy in the bomb has been converted into heat and sound and light and kinetic energy of the fragments of the bomb, right? So total energy is still conserved. I'm not saying the law of conservation of energy doesn't hold, but we don't have equations for things like thermal energy, chemical potential energy. They're not easily tracked in our system. So it's not a very good way to analyze these, right? Again, consider a firecracker that's at rest, explodes into two pieces. Initially, it was at rest, so it had no kinetic energy. After the explosion, both pieces will be moving quickly, and therefore both have kinetic energy. So there is no way for an explosion to be an elastic interaction. It will always be inelastic. There's no chance at kinetic energy being conserved, okay? So in all three of these interaction types, elastic, inelastic, and explosions, total momentum is conserved. So again, it's not that conservation of energy is not true, but it's not always useful for analysis because energy is really good at escaping in forms that we can't really track and don't have equations for, right? Thermal energy going into the atmosphere, sound energy going into the atmosphere, right? All of those we don't have equations for them and we can't keep track of them very well. Momentum will always work. Conservation of momentum will never fail us. Okay, let's try out an example here now. Our first one where we're actually going to take the law of conservation of momentum and do what we know we can do with it, which is use the conditions before to figure out what will happen later, or vice versa. Use what's happened after to figure out what must have been happening before. Let's go. All right, so a quarterback and a linebacker collide on the football field. Each player has a mass of 75 kilograms. Okay, so they have the same mass. That won't always be true, but in this case they do. The quarterback was running east at 3.2 meters per second, while the linebacker was running west at 2.4 meters per second. They do not stick together when they collide. After the collision, the quarterback has a velocity of 1.1 meters per second to the west. What is the velocity of the linebacker after the collision? So diagrams are really helpful here for keeping track of all this information. So just note here, right? We have the mass of each player, and we have both of their velocities before the collision. So we actually have all of the momentum information we would need for before, right? For before, we've got each player's mass and each player's velocity. So we can get each player's momentum. Momentum is just mass times velocity, right? Afterwards, we have one of their velocities, so we have one of their momentums. Can we figure out the other one's momentum? Well, we can because we know the total has to be the same. But I'm getting ahead of myself here. Let's just draw our diagram first, okay? So before, we had the quarterback running east. I'm just going to use Q for quarterback and L for linebacker. So we had the quarterback, their initial velocity, so V quarterback initial, okay, was to the east. I'm just going to draw it as an arrow for now. I'll do the numbers off to the side so it doesn't get too crowded. And then we have the linebacker who was running west. So V linebacker was to the west initially, okay? Now, afterwards, we don't know the quarterback's velocity. We do know the quarterback's velocity. We don't know the linebacker's velocity. That's what we're trying to figure out. So afterwards, it tells us that the quarterback is moving 1.1 meter per second to the west, right? So that's V quarterback final. So they're moving to the west. V quarterback final. What we want to know is how is the linebacker moving after the collision? Now, we don't actually know for sure if it's going to be to the east or to the west. My gut says probably to the east, just to keep momentum conserved, but it's possible that the total momentum was to the west to begin with. We'd have to actually do the calculation, although we can see the linebacker was running west slower than the quarterback was running east, and since they have the same mass, that means the quarterback has the greater total momentum, right? Their mass times a bigger velocity gives them more momentum. So we actually do kind of know that the initial momentum overall was to the east. This eastward momentum is bigger than this westward momentum. So that if we think about it enough, that does actually tell us that the linebacker must be moving to the east. We just don't know how fast, okay? Again, we don't actually need to do that thought process there, but it doesn't hurt, because what we're about to do is do the calculation, and the calculation will tell us that it was moving to the east as well. But good to just throw some logic in there, right? That's what we want to know, okay? So let's just make a list of our givens here. We know that the mass of the quarterback and the mass of the linebacker is 75 kilograms, right? We're going to need that to think about their momentum, because momentum is mass times velocity, okay? Now, two objects before, they don't stick together, so still two separate objects after. That means we essentially have 4 total momenta to think about, right? 2 momentums before, 2 momentums after, and therefore 2 velocities before, 2 velocities after. So let's go ahead and say, okay, the velocity of the quarterback initial. We know that. That is 3.2 meters per second. To the east, I'm going to go ahead and call east positive and west negative. Again, Not mandatory. We could just as easily call west positive, but then we would need to make east negative. Remember, opposite directions just need opposite signs. That's the tool we use to make sure that our math works out, and vectors in opposite directions do cancel each other out. Okay. We also have the velocity of the linebacker initial. That is 2.4 meters per second to the west. So the velocity of the linebacker initially, we're going to say we're calling west negative, so negative 2.4 meters per second. Okay, and then we also know the velocity of the quarterback after the collision. So we know v quarterback final is 1.1 meter per second to the west. So west is negative, so we're going to say negative 1.1 meters per second. Okay, and what we're trying to figure out is how fast and in which direction would the linebacker be moving after this collision. Okay, so how are we going to do it, right? Again, don't get overwhelmed. We're going to start simple. In fact, we could even have started here before we did the diagram and all that and wrote out all our givens, right? Because it's always the same thing. The law of conservation of momentum, physics principle number 4, says that the total initial momentum will equal the total final momentum. Whenever a student says to me, I'm not sure how to start this one, I say, well, this is how you're going to start it, right? It's not even a question. This is how we should start a conservation of momentum problem, right? This is always going to be it, okay? The total momentum initial has to equal the total momentum final. That's the basic physics principle we're applying here, okay? And then we can start thinking about it. Okay, so what is the total momentum initial? What are the objects we have initial? Well, we have two. We've got a quarterback and we've got a linebacker. So let's take that one step further then. The total momentum initial is just the momentum of the quarterback initially plus the momentum of the linebacker initially. What's the total momentum final? Well, again, we've got two objects, right? The quarterback has a final momentum and the linebacker has a final momentum. So their two momentum initially added up will equal their two momenta finally added up. Okay, now we weren't given their momenta, but we were given their masses and their initial and final velocities, right? So momentum, don't forget, is just mass times velocity. So what's the quarterback's initial momentum? It's the mass of the quarterback times their initial velocity. Mass quarterback times velocity quarterback initial. What's the momentum of the linebacker initially? Well, the mass of the linebacker times the linebacker's initial velocity. Same thing for the final, except obviously using their final velocities, right? So far all we've done, we said total initial equals total final. Total initial is just the quarterback plus the linebacker initial. Final is quarterback plus linebacker final. And then we've broken each of those P's down into their corresponding MVs, right? Momentum of the quarterback initial is mass quarterback times the quarterback's initial velocity. Mass of the linebacker final is the linebacker's mass times the linebacker's final velocity, right? And look at this. If we go through this equation, what do we know? We know the mass of the quarterback. We know the mass of the linebacker. We know the quarterback's initial velocity and the linebacker's initial velocity, right? We know the quarterback's final velocity, so the only thing we don't know in this equation is the linebacker's final velocity. If the only thing we don't know is one thing, we can solve it with this equation, right? Isn't that cool? The power of the law of conservation of momentum. Just by knowing about how things started and some piece of how things ended up, we can figure out the other things that we don't know about how it ended up, because we know the total momentum had to stay the same. Okay, so now we need to isolate for the required variable, right? We just need to isolate for the linebacker's final velocity, because that's what we're looking for. So don't forget, reverse order of operations, okay? We're undoing all the operations that are happening to this linebacker's final velocity. So it's being multiplied by its mass, that's true, but it's also being added to this. So before we deal with the multiplication and division, we're going to have to deal with the addition. So let's subtract the quarterback's final momentum here from both sides. So doing that got me here, okay? Just subtracted MQ, VQ final from both sides. This actually makes a ton of sense because look, this right here represents the total initial velocity, the total initial momentum, right? And we're saying if we take away the quarterback's final momentum, what we should be left with is the linebacker's final momentum, right? Well, that makes sense because we know the total initial has to equal the total final, but the total final is split between the quarterback and the linebacker. So take the total initial, that's the same as the total final, and take away whatever of the final is with the quarterback, and you're left with what must be in the linebacker. Okay, anyway, we're continuing to isolate the velocity of the linebacker final. Now there's only one operation being performed to it. It's being multiplied by the linebacker's mass. So how do we undo a multiplication by the linebacker's mass? We need to divide both sides by the linebacker's mass. So doing that will get us to here, right? And there we go. We've isolated. We know all this stuff. All that's left to do is plug in and calculate. Just be careful. Don't forget about your direction stuff, right? We called west negative. We called east positive. So plugging in our numbers now, okay? This is why it's always nice to make a list of your givens too, because now we've just got this nice, neat list. When we need a variable, we can go reference it rather than having to reread the question and perhaps miss stuff or make a mistake. Okay, so mass of the quarterback, 75 kilograms. Initial velocity of the quarterback, positive 3.2 meters per second. Plus, mass of the linebacker was also 75 kilograms. And the linebacker's initial velocity was to the west, so be careful, negative 2.4 meters per second. Minus the mass of the quarterback again, so 75 kilograms, times the quarterback's final velocity, which was to the west, and it was negative 1.1 meters per second. And we're going to divide all of that by 75 kilograms. Won't always work out this way, but we could notice that this term has a 75 kilograms, this term has a 75, and this term has a 75. So we actually could just cancel the 75 out there. I'll just go ahead and calculate from here, though. So for my numerator, I got, multiplied these all together and then added these and subtracted that. And I got a positive 142.5 kilogram meters per second. That's my numerator. I wouldn't recommend trying to put this all in your calculator in one big step. That's how mistakes happen, right? Break it up into smaller pieces. Enter a part, enter, write down the result, right? Enter another part, hit enter, write down another part. But that's where I got to. Sure enough, kilograms over kilograms. We're going to be left with meters per second. That's a good sign because we know that we're looking for a velocity, so we should be getting units of meters per second out. And then when I did that, when I calculated 142.5 divided by 75, I got that the velocities of the linebacker final is going to be positive 1.9 meters per second. Okay, so let's do some checks here. Does that make sense? Does a positive velocity make sense? I mean, that's kind of what we predicted, right? Because we said looking at the numbers here, we can tell that the quarterback has more momentum, bigger, same mass, but a bigger eastward velocity. Meaning that if out of these two momenta, the bigger one is to the east, then the east kind of wins, right? And overall, the momentum is to the east, right? So since the quarterback was moving to the west final, the linebacker must be moving to the east to preserve that eastward momentum. So that's a good sign that we got a positive. The number also seems reasonable, right? 1.9 meters per second to the east, negative 1.1 meters per second for the westward one. So it is bigger, but it's not like ludicrously bigger because initially the momenta weren't ludicrously different either, right? So I feel pretty good about that. Now, last thing, velocity is a vector, so I can't just say 1.9 meters per second if I can actually interpret that positive. And in this case, I can interpret the positive. The positive meant east. So there we go, okay? Now, I know the equation might get a little scary looking, right? But all we're doing here is applying this idea, right? And then it's just some algebra. I'll mention too, some students like to break it up a bit. Rather than putting it all into this equation like this, some students like to just calculate the momentum of the quarterback, calculate the momentum of the linebacker here, calculate the momentum of the quarterback here, and then just put those numbers in and then kind of break it up into multiple steps. Okay, that's totally okay. It will work for most questions. There might be some where you don't know something, so you kind of do need to keep all of the variables and hope for cancellations and stuff, okay? But there is more than one correct approach here, right? You could just do MV, get the number, MV, get the number, MV, get the number, and then just put your numbers in and solve for the linebacker's final momentum maybe, and then divide it by the linebacker's mass, right? More than one approach we can take, but they all involve applying this fact, the law of conservation of momentum. This is where we start, right? Then we break it down and get more specific to our problem. Okay, let's look at B. B asks, is this an elastic or inelastic collision? Confirm with the necessary calculation. Well, what is the necessary calculation? Pop quiz. What makes a collision elastic? In an elastic collision, kinetic energy is conserved, right? That's it. That really is it. In an elastic collision, kinetic energy is conserved. In an inelastic collision, it's not, okay? Technically, truth be told, there's a little more to it. In an elastic collision, it's mechanical energy is conserved. However, in physics 30, we just kind of keep it to kinetic energies, okay? So in an elastic collision, what does that mean? If kinetic energy is conserved, it would mean that the total initial kinetic energy should equal the total final kinetic energy, right? So if we want to check if this is an elastic collision or an inelastic collision, that's the calculation we have to do, right? I'm putting a question mark just saying, is this true for this collision, okay? We can't rule it out on the basis of like, oh, it's not the right type, because it is. They hit and bounced. They didn't stick together. So it is possible that it could be. We'll need to do the calculation to confirm here, okay? But it's the same idea. We have two objects, each moving, each with mass, so they each have kinetic energy before and after. So the initial kinetic energy total is going to be the quarterback's initial kinetic energy plus the linebacker's initial kinetic energy. For the final, you guessed it, two objects, both moving, so energy kinetic of the quarterback final plus energy kinetic of the linebacker final. Now we know that to calculate the kinetic energy of an object, right, we take its mass times its speed squared and divide it by 2, right? Kinetic energy is 1/2 of mv squared. So what's the kinetic energy of the quarterback initial? Well, it's their mass times their initial speed squared over 2, right? What's the kinetic energy of the linebacker initially? It's the mass of the linebacker times their initial velocity squared over 2. Sorry, I said velocity there. For energy, it's their speed, right? Same number, but we're not worried about direction. For the finals, same story, right? Just breaking their kinetic energies down into the correct equation, okay? And we've got all this information. So we really are just checking here, right? We could have done it as two separate, like initial and then done final and compared the two numbers. I just set it up and to see, you know, are these equal, okay? Are they? So let's put in our numbers here. The mass of the quarterback, 75 kilograms. Their initial speed, no positives, no negatives here. We're talking scalars, right? So their initial speed is 3.2 meters per second squared over 2. Linebacker, 75 kilograms. What was their initial speed? It was 2.4 meters per second, right? Yes, it was to the west, but we're talking speed here. We're not worried about direction. So it's just 2.4 meters per second. It's a scalar. Okay, so we'll calculate the left side and we'll calculate the right side. And if they're the same, it was an elastic collision. If not, it was inelastic. Let's put in our numbers on the right side here for final. So putting in the numbers there, I also decided to add some color coding here so we can more easily see this is just what it was initially around. This is what was finally around in green there, okay? We're going to calculate the left side, calculate the right side, see if they're equal or not. Note, too, that we used our the velocity of the linebacker final, well, the speed now, that we got from our conservation of momentum, right? That's allowing us to complete this calculation, okay? Truth be told, we can kind of see that this is headed towards being inelastic, right? Because look, 3.2 squared, 2.4 squared, these are both bigger numbers squared. The mass is 75, so it seems like we had more kinetic energy before than after. Sure enough, after calculating those parts out, right, and looking at it, we can really see that this isn't looking like it's going to be elastic. Before, we had 600 joules of kinetic energy. Afterwards, it looks like we've got 180.75 joules of kinetic energy, right? So, was kinetic energy conserved? No, right? Initial does not equal final, okay? So they are not equal. So since total initial kinetic energy did not equal total kinetic energy final, right? It is an inelastic collision. That's it. That's the definition of an inelastic collision. Kinetic energy was not conserved. Now, was kinetic energy destroyed? No, it would have been converted into other forms like heat and sound and stuff. So conservation of energy is still true. That is a law of physics, right? But no one said it had to stay as kinetic energy, and nobody said it had to stay in our system. So total energy was conserved, but it might have left the two football player system that we're looking at here and or changed into other forms besides kinetic. Okay, so this is an inelastic collision, and total kinetic energy was not conserved. Okay, let's try this one out. So taking a look here, looks like we've got a diagram for before and after. We see that there's a compressed spring between these two masses. The masses are being held together by a rope right now, and neither of them are moving, right? So velocity 1 is 0 meters per second, velocity 2 initial is 0 meters per second. Afterwards, they cut the rope, and as a result, they shoot away from each other, right? That spring pushes them away from each other. So this is essentially an explosion, right? I mean, might not be like a bomb going on, but from a physics standpoint, this is an explosion. We had one big object that's now split into two. So it asks us, what is the speed of the smaller box after the rope has been cut? State the physics principle used. So we weren't actually given the masses here, right? But we were given that this one is triple the mass of this one. So if this is mass m, then this is just 3m, right? And we are given their velocities before and after, okay? Now, we definitely couldn't use conservation of energy here, not because it's not true, but because we don't really have the information we need, right? We don't know if we can tell kinetic energy was not conserved. We don't know enough to know what the spring potential of this would be. So this is a good one where we could use conservation of momentum, and that will definitely still work. So let's start there, right? Let's not get ahead of ourselves. Always start general, apply the basic physics principle, apply what we know about how the universe works, and then we can apply that, get more specific to this situation. So I don't know where we're headed, but I do know that the total initial momentum will be equal to the total final momentum in this system. Okay, that's always going to be true. It's a law of the universe. So total initial momentum will equal total final momentum. Okay, well, we can simplify this right off the bat because what is our total initial momentum, right? It's 0. Neither of our objects are moving, right? So mv is mass times 0. So actually, right away, we can just say 0 is our initial momentum. Now that has to equal our final momentum. Final has a little bit more going on. We've got an object moving to the right with a velocity of 2 meters per second, and an object moving to the left with a velocity unknown. That's actually what we're trying to figure out. But we have two objects, so we have two momentums to think about, right? But add up, this is saying it's the total final momentum. That's what this is saying. So add up all of the objects' momentum. We've got two objects, so momentum 1 final plus momentum 2 final. And those have to equal 0 because there was no momentum in the system initially, right? So if we continue down this path here, 0 is equal to momentum 1 final, so that's m1 v1 final, right? P equals mv. Momentum 2 final is mass 2 times velocity 2 final. We are interested in finding object 1's final velocity. We were given object 2's final velocity, so we just need to isolate this, right? So what will we do? We'll subtract m2 v2 final from both sides, and then we'll divide both sides by mass 1, right? Undoing the operations that are happening to our required variable, v1 final. So subtracting object 2's momentum from both sides gives us a statement. Look at this. This is the physics speaking to us through the math, right? This statement here actually makes a ton of sense. If there was 0 momentum initially, which we know there was, right? And then afterwards, one of the objects does have momentum, the other one must have the same amount of momentum, but in the opposite direction, so that momentum is conserved, so that total initial momentum equals total final momentum, right? If we were to draw a vector addition diagram here, we know they have to still add to 0. We can see that object 2 has a momentum to the right, Object 1 must have a momentum just as large to the left so that the resultant, the net momentum, is 0. Okay, going back to solving this here now, we're solving for V1 final. It's being multiplied by mass 1, so let's divide both sides by mass 1, and here we go. We get that V1 final, the final velocity of object 1, is equal to negative m2 v2 final over mass 1. Let's go ahead and plug our numbers in. V1 final is equal to, okay, now we don't have numbers here, but we do know that mass 2 is 3 times larger than mass 1, right? So we can take advantage of that because, right, it just has 3 times the mass. So since we're dividing their two masses here, we might note that, okay, well, this factor of m is just going to end up canceling out, right? Look, negative mass 2, but we know that's just been stated as being 3m, right? Whatever m is, we don't actually have a number. Okay, whoops, times v2 final. We do know v2 final. I'm going to call that direction positive, that direction negative. So positive 2 meters per second is object 2's final velocity divided by mass 1. Again, don't have a number, but we're told it's just some number m, some mass m. Okay, and look at this. V1 final is therefore equal to, well, mass, again, we don't know what it is, what this value m is. Could be 10, could be 100, could be 0.1, but it still cancels out because we just know that this is 3 times as massive as this one. So for momentum to be conserved, right, it's the ratio of these two that ends up being important. So let's get our answer, and then we'll see if we could have predicted this answer. Okay, because you can see that our answer is about to become negative 3 times 2, or negative 6 meters per second, right? Now, we weren't told anything about like left, right, east, west, so a negative is actually okay here, and we actually do only get 1 sig dig because they only gave us 1 sig dig for this velocity, so we can just say negative 6 meters per second. But let's return to what I was saying there. Could we have predicted this beforehand if we thought about it? Okay, I think we actually could have, because remember, the two things that we need to make a momentum are mass times velocity, right? Now, because of the law of conservation of momentum, we know that the total momentum after had to be 0, right? Because the total initial momentum was 0. Now, this thing has 3 times the mass, and it's moving at 2 meters per second. So if momentum is mass times velocity, right? The fact that it has 3 times the mass would give it 3 times the momentum if the velocities were the same. Therefore, the velocities cannot be the same, right? Because this has to have the same amount of momentum, but in the opposite direction as this one, so that they cancel out to 0. So another way to say that, if this has 1/3 the mass as this one, to make up for that, it must have 3 times the velocity, but in the opposite direction, right? Sure enough, this was moving at 2 meters per second to the right, so this one had to move at negative 6 meters per second, right? 3 times faster than this one to make up for the fact that it only had 1/3 the mass, so that they can have equal but opposite momenta, cancel each other out, and give us what we know the total final momentum had to be, 0, because that was our initial total momentum. Cool, right? Okay, so in this one, we've got a 4 kilogram block of putty being thrown at a speed of v. So they're not telling us the speed. It hits and sticks to a stationary block of ice with a mass of 12 kilograms, and we want to figure out what its new speed is. We might not be able to figure out the number, but we can figure it out in terms of the initial speed at least. Let's just draw our before and after diagrams here to get our bearings. So before, we've got this ball of putty being thrown at a speed of v, and it hits a stationary block of ice. Okay, so I'll say that v block initial is 0, right? And therefore its momentum is 0, so that's nice. Whereas our ball of putty here, we've got it moving this way. I'll say P for putty. V putty initial is, don't know the number, but they're just telling us it's v, okay, the variable v. So what does the momentum look like initially? It's to the right, right? And right now it's kind of entirely in the block of putty, right? So our total initial momentum is just to the right. It's all kind of in the ball of putty right now, right? It looks like that. It's all coming from the putty. Now afterwards, it's going to hit the block of ice and they're going to, move together, right? They're going to move together as essentially now one object, right? Now, if the momentum is to the right here and about this big, without even thinking about it, what's the momentum like here? It's the same, right? It's about that big and it's to the right. So the momentum final, total momentum final, will be similar. It'll be not similar, it'll be identical. Whoops, it looks like I drew it a bit too big there. Okay, so what we're trying to figure out is what is the velocity of this system now, right? The putty and the block move together as one object. So question for you, would you expect this new velocity to be the same size as v, bigger than v, or smaller than v? Okay, a common student mistake here is to say that the velocity will be the same, right? But think about it, that doesn't make sense because there's now more mass that's moving, right? It used to be just 4 kilograms that are moving. Now it's 16 kilograms. That's just 4 plus 12, right? Their total mass is moving. So if the velocity stayed the same as the putty's velocity, we would be violating the law of conservation of momentum because momentum is mass times velocity. So if the moving mass got larger but velocity stayed the same, we would have created momentum out of nothing, right? So let's revisit that question then. The amount of mass that's moving got larger. What would you predict? And you can even draw on your regular day experience here, right? What would you expect? Would you expect this now to be moving slower than the putty or faster? It should be moving slower, right? Our mass has increased. So to keep momentum the same, the velocity must decrease, okay? So we're trying to figure out what that new velocity will be. I'm going to say VPB. That's for putty block, okay? Because it's now really one object. It's the putty and the block of ice stuck together. We want to figure out what its new velocity would be in terms of that initial speed v, okay? Now, what I say, we're always going to start simple here, right? What's the basic idea that we're going to apply to solve this? The basic idea is that the total initial momentum will equal the total final momentum. So initially, we have, kind of two objects here. We could think of it that way. We've got the putty ball and we've got the block of ice. Now, the block of ice isn't moving, so if we want, right now, we can say, well, it's not moving. Its velocity is 0, so the momentum is 0, right? Mass times velocity. If the velocity is 0, then momentum is 0. Now, afterwards, we kind of have this system of a putty ball and a block of ice, okay, that are moving together as one object. And its momentum, this one object's momentum, must be the same as whatever momentum was initially in the system here in the block of putty. So that means that the initial momentum of the putty must be equal to the final momentum of when they're both stuck together. So from here, let's now break these P's down into MVs. So what's the momentum of the putty initial? Well, it'll be the mass of the putty times its initial velocity. And that's going to need to be equal to, what's the mass of the putty block system when they're stuck together? Well, we do have a mass, right? It's an object with mass. It's the mass of the putty plus the mass of the block of the ice. So mass putty plus mass block of ice times their combined velocity, right? They're stuck together now as one object that moves with one velocity. And what we're trying to find is this, the velocity final that they move together with. So ask ourselves, what is happening to it? Why is it not isolated? It's being multiplied by their combined mass. So if we divide both sides by their combined mass, we get this, right? The mass of the putty times the putty's initial velocity divided by their mass combined should give us the velocity that they move together with afterwards, right? This is just the total initial momentum that was in our system afterwards, there's only one object, so divide by its mass, and you should be left with its velocity, because those two momenta need to be the same. All right, so before we plug in numbers, I want to make a prediction here. Always good to make predictions, because then that can help you, when you get your answer, you can say, okay, yeah, that makes sense, right? Rather than just kind of hoping for the best. Okay, but look, 4 kilograms was moving before. We can now see that there's about to be 16 kilograms moving, right? And we know that the momentum had to stay the same. So the mass has gone from the moving mass anyway, has gone from being 4 kilograms to being 16 kilograms. So the moving mass has gotten 4 times larger. Now to keep momentum the same, what would we need to do to the velocity to keep momentum the same, right? If mass got 4 times larger, that on its own would give us 4 times more momentum, which we know can't be true. Otherwise, that would be creating momentum out of nothing, right? So what must happen to the velocity? I'm going to predict that the velocity should end up being 1/4 as large as the putty's initial velocity. So yes, the mass got 4 times bigger, but momentum is conserved, so the velocity would need to become 1/4 as large. So that overall, momentum stayed the same, right? 4 times 1/4 is just 1, leaving us with the same total momentum. Let's see if it works out that way. So the velocity final of the putty ball system is going to be, let's just put in our numbers, 4 kilograms was the mass of the putty. Its initial velocity, we don't know that, but we know it's v, okay? And their combined mass, the total mass of the thing that's moving now is, well, 16, right? 4 plus 12. 4 kilogram putty, 12 kilogram block of ice. So doing that, sure enough, look at this. We get 4 kilograms times v over 16 kilograms. Kilograms over kilograms, those cancel out, and we're left with 4/16 of v. Well, 4 over 16, that's a reducible fraction, right? They're both divisible by 4. 4/16 is equivalent to 1/4. 1/4 v, right? Or v over 4 if you like. Okay, so sure enough, it checks out, right? Now again, we can't get an actual number because they didn't tell us how fast it was moving initially. But however fast it was moving initially here, we know that together they will be moving 1/4 as fast. So if it was moving 100 meters per second, it's now moving 25 meters per second, for example, right? If it was moving 8 meters per second, it's now moving 2 meters per second together as a system. Okay, so we can't get a number, but we can get that it's 1/4 as large. Makes sense because the moving mass became 4 times larger. So for momentum to be conserved, the velocity must have gotten 4 times smaller. It's essentially this situation here, right? Red cart, 4 meters per second, mass 1 kilogram, so 4 kilogram meters per second of momentum. Blue car, at rest, no momentum. So it comes in, boom. Now they move together, so total mass moving is 4 kilograms. To keep there being the same amount of momentum, they both slowed to 1 meter per second, 1/4 the velocity they had before. Cool, right? So just be aware again, be careful. A common student mistake with these is to act like there's a law of conservation of velocity, right? There's no law of conservation of velocity, law of conservation of momentum. So mass times velocity needs to be the same before and after, total for all objects. All right, let's try this one here with a cannonball explosion. So A just asks us, without even calculating anything, it just asks, could this be an elastic collision, right? So what's the situation we're looking at? We've got a cannon with the cannonball in there somewhere, and then after, we've fired the cannonball, right? And so the cannon is recoiling backwards. This is where recoil comes from. It's actually a consequence of the law of conservation of momentum, right? Shoot something forwards really fast, give it momentum. Well, total momentum has to be conserved. So the cannon here is going to recoil backwards because initially there was no momentum, right? Now there is a lot of forward momentum for the cannonball, so there has to be some backward momentum for the cannon to give us still 0 momentum total, because that's what we started with. Now, could this be an elastic collision? Well, remember, pop quiz, what is conserved in an elastic collision? Momentum is always conserved. What other quantity has to be conserved to make a collision elastic? Right, it's the kinetic energy, the total kinetic energy. Remember, kinetic energy is a scalar. So forward kinetic energy is not a thing, right? It's just kinetic energy. Whether it's forward, backward, whatever, it's all just kinetic energy. So this isn't positive and this isn't negative, right? So, for kinetic energy anyway. Okay, so could this be elastic? Could kinetic energy have been conserved? No, right? Before we had none. Nothing was moving. Afterwards, we have a whole bunch of kinetic energy. This is moving very fast forwards. This is moving backwards. They both have mass. There's a whole bunch of kinetic energy that was not there before. It wasn't created out of nothing. It came from kinetic or chemical potential energy in the gunpowder and heat and stuff like that, right? But kinetic energy was not conserved. There is no way this could be an elastic interaction, right? No calculation necessary to show that total kinetic initial doesn't equal total kinetic final. There's no way it could. There was 0, and now there's definitely not 0. So no. So just kind of wrote out what we discussed there, right? The cannon and the cannonball were both stationary initially, so there was no kinetic energy. Afterwards, there's a whole bunch. If the total initial kinetic does not equal the total final kinetic, it is an inelastic collision, right? Energy wasn't created out of nothing. It was from chemical potential energy into kinetic, but kinetic energy not conserved, not an elastic collision. Now, B asks us if the momentum of the cannonball after being fired is 15 kilogram meters per second to the right, what is the momentum of the cannon after firing the cannonball? Well, we can actually just think about this because, okay, initially, neither is moving. P equals mv. If v is 0, our total initial momentum is 0, right? So without even thinking about it, what must be our total final momentum? 0. It must be the law of conservation of momentum, right? So with that in mind then, if the cannonball, they're telling us that the ball has a momentum of 15 kilogram meters per second to the right, how do we keep it so that the total is 0 kilogram meters per second? Well, the cannon must have 15 kilogram meters per second of momentum to the left, right? It must be. Or if we're calling right positive and left negative, negative 15 kilogram meters per second. So that the total momentum in our system is 15 plus negative 15, giving us the same total we started with, 0, right? So no way around it. The momentum of the cannon must be 15 kilogram meters per second to the left, right? Otherwise, momentum would not be conserved. Total initial was 0. That has to be the same as the total final, right? We can use a VAD here as well, a vector addition diagram, right? We could say, okay, momentum of the ball final, add that tip to tail with the momentum of the cannon final so that they perfectly cancel each other out and our net momentum vector is 0. Okay, now C asks us, why can't we use the law of conservation of energy here? Well, again, it's not that the law of conservation of energy isn't true here, but do we have an equation for chemical potential energy, right? Because that's a lot of what is causing the cannonball to be fired. It's gunpowder. That chemical potential energy contained in the gunpowder is being converted into thermal energy, which is then being converted into the kinetic energy of the cannonball, right? We don't really have equations for that stuff. Plus, we don't have any way of knowing how much of that energy actually went into the cannonball and how much just left the system as heat energy altogether, right? So again, it's not that the law of conservation of energy isn't true, but we don't really have the information we would need to use it. We have no way of knowing where that energy all went. It's hard to keep track of, so to speak, unlike the momentum in this situation. Okay, so just jotting that down there. The energies that we actually have equations for weren't conserved here. Total energy was conserved, but like kinetic energy wasn't, right? Gravitational potential energy might not have been, spring potential. Those are the only things we actually have equations for, right? They weren't conserved. The total kinetic energy does not equal the total final kinetic energy, right? And again, it's been converted from or to forms that we can't analyze. We don't have an equation for thermal energy or for chemical potential energy. And what's more, it might have even just left the system altogether, right? A lot of that initial chemical potential energy will have left as heat and sound, right? That's a problem we don't have to worry about here with momentum. But we could not have solved this by saying total kinetic initial equals total kinetic final, because it doesn't. Again, total energy was conserved, but it's gone into forms that we can't keep track of. Okay? All right. So in this one, a car rear ends a truck. Due to the forces involved, the truck feels an impulse of 600 newton seconds. What is the impulse felt by the car? Explain your answer using Newton's third law and conservation of momentum, which we know are two very closely related ideas. In fact, this leads to this, okay? But let's try and do it both ways. So, Newton's third law, what does it say? It says that they will exert equal but opposite forces on each other. So, as long as they're in contact, right, they'll be, however hard the car is pushing forward on the truck will be pushing backwards on the car. Now, they have to be in contact with each other for the same amount of time, right? How could the car be in contact with the truck for a different amount of time than the truck is in contact with the car? If one's in contact, they're both in contact with each other. So they're in contact for the same amount of time and therefore exerting that equal but opposite force on each other for the same amount of time. Now, forces exerted for a time, we know those can cause an impulse, a change in momentum, right? So the truck felt an impulse of 600 newton seconds, okay? Let's think about the car now. The car was experiencing the same force, just in the opposite direction as the truck, right? For the same amount of time. So this force is the same magnitude, I should say, same magnitude, just opposite direction between the truck and the car. And the time is just the same. So what can we say then if impulse is just force times time? They felt the same force, just in opposite directions, for the same amount of time. Well, the impulse is also going to be the same magnitude, but opposite direction, right? The impulse will also be equal but opposite. So if the truck felt an impulse of 600 newton seconds, the car is going to feel an impulse of negative 600 newton seconds, right? If the truck's impulse was 600 newton seconds to the right, the car must feel an impulse of 600 newton seconds to the left. All right, so if the truck felt impulse positive 600 newton seconds, right, the impulse must be equal and opposite, since the forces are equal and opposite and the times are the same that they're in contact for. So the car must experience an impulse of negative 600 newton seconds. Same size, opposite direction. Now, can we get the same result by just thinking about the law of conservation of momentum? We should be able to, because really, as we saw at the beginning of this lesson, the conservation of momentum really just comes from these ideas here, thinking about Newton's third law, right? Okay, so for momentum to be conserved, what needs to be the total overall impulse of the system? We know that, like, individually each object can have an impulse, a change in momentum, but for total momentum to be conserved, which we know it always is, right? What is the overall impulse of the entire system? It's got to be 0, right? So just writing that out there, the total impulse, change in momentum, needs to be 0 for momentum to be conserved, right? Overall, the total momentum in the system has to change by an amount of 0, otherwise it changed and wasn't conserved. So if the truck experiences a change in momentum of positive 600 newton seconds, the other object in our system, in this interaction here, the car, must experience a change in momentum of negative 600 newton seconds, so that they cancel each other out and the total change in momentum is back to 0. Right? Now, again, that doesn't mean the momentum is 0. It means the total change needs to be 0. Otherwise, well, the overall momentum changed and it wasn't conserved. The total impulse needs to be 0 here, right? 600 plus negative 600 gives us 0, which we know needs to be the case for momentum to be conserved. So there we go, right? Two different ways of thinking about it. I mean, sort of. They are very closely connected and at the end of the day are kind of the same idea, right? But with Newton's third law, we see that the car had to feel an impulse of negative 600 Newton seconds if the truck felt one of positive 600 Newton seconds, and also via the conservation of momentum. This just gained 600 Newton seconds of forward momentum. That's only possible if the car lost 600 Newton seconds of forward momentum so that the total didn't change. Okay, so time to take a little break from my voice, pause the video for a while, right? Again, I know these can get kind of long because we're covering all of Physics 30 in one quarter. This is typically what would fit into like a 3-hour class. So that's why the lessons are spaced out a bit with a day or so in between each one. You might even pause here, do some practice for a bit, and then use your second day to kind of finish this up, right? Break it up a bit. But either way, at the very least, try this example here. Okay, again, the solutions are always posted in the agenda. And you can work through, see how it goes for you. Try a few other ones on the page as well if you like. Well, maybe not even if you like. I would really recommend doing that, okay? But yeah, go ahead. Try applying the law of conservation of momentum. Remember, always start in the same place. Okay, this is a conservation of momentum one. So start there. Add up all the initial momentum. Set it equal to all the final momentum, right? Figure out, okay, what objects do we have initially? What objects do we have finally? Right? Momentum 1 plus momentum 2 initial equals momentum 1 final plus momentum 2 final. Solve for what you're trying to find in each of these cases. Okay, let's give that one a try and then we will finish up here with a couple more examples. So this section here is just talking a little bit about when can you use conservation of momentum and when can you use conservation of energy, okay? Well, the short answer is you can always use conservation of momentum. It is always safe to use the law of conservation of momentum, okay? Now, around that time, students often say, well, why would I ever use conservation of energy then? The answer is you'll see in the next lesson when things get two-dimensional, because momentum is a vector, it has x and y components, and that can mean they take a little bit longer to solve this way. So sometimes if we can get away with it, it can be nice to use the law of conservation of energy. I'll be honest though, Physics 30, they're mostly testing momentum because conservation of energy, while it comes up in Physics 30, it's technically you learned it in Physics 20. So this is the one that comes up more often anyway. So when in doubt, you can always use the law of conservation of momentum. But how do you know? Like, how do you know when you're safe to use momentum and when you're safe to use conservation of energy? Okay, well, if we take a look here, okay, just a sample question, like let's say it said, in an isolated system, a white cue ball collides with a black 8 ball as shown. The collision is a blank collision. So I'm just saying there would be a word there that would tell us which one we could use, right? Determine the final blank of the cue ball. There'd be a word there that would tell us whether we can use conservation of energy or whether we have to use conservation of momentum, okay? So that first blank, the clue that would go there would be elastic or inelastic. If it is an elastic collision, that means there's no mechanical energy and really no kinetic energy lost, right? By telling us it's elastic, they're saying that total initial kinetic energy equals total final kinetic energy, right? And so therefore, this could be our starting point. We could just go with this, right? Conservation of energy may be used, though we could still use conservation of momentum. It can always be used. So then it just comes down to personal preference, right? If it was an inelastic collision, however, it indicates that kinetic energy was lost, right? It left the system. It wasn't destroyed, but it did leave our system. So we can't say that the total initial kinetic energy of the cue ball is going to be the same as the total final kinetic energy. It's going to be lost as, heat through the action of friction, sound, damage, things like that. So you cannot use a conservation of energy calculation there, right? Not that energy hasn't been conserved total, right? Energy just has not been conserved within the system. At the very least, the forms of energy that we actually have equations for and can analyze have not been conserved within the system. There are unknown energy values elsewhere, right? It's left. So conservation of momentum may always be used. So in that case, we're going to have to go with the conservation of momentum there, right? In this case, we would have to use physics principle number 4, the law of conservation of momentum. In this case, we could have our choice. We could use physics principle number 4, conservation of momentum, Or we could use physics principle number 5, which on the back of your formula sheet you'll see is the law of conservation of energy. What about that second word there? Determine the final blank of the cue ball. Well, that would be if we were asked to find the final speed of the cue ball. Speed is a scalar, right? So we don't actually need to know which direction it's moving. We just need to know how fast it's moving, okay? Energy is a scalar, so it will not give us direction, right? We know that kinetic energy has no direction, so it can't tell us the direction the object was moving. Momentum will give us both. So if we were asked to find the speed, that's fine. We could get away with using energy as long as we know it's also an elastic collision, right? So if this says elastic and this says speed, we can get away with finding or using law of conservation of energy, right? Because we have equations for all the energies before and after, and we don't care about the direction it's moving. We just want to know how fast it's moving. Okay, so in this case, if it asked for speed, we'd have our pick. Once again, we could use conservation of momentum or conservation of energy. Okay, however, even if it told us that it was an elastic collision, but then it asked us to find the final velocity of the cue ball, we're going to have to use conservation of momentum, right? Because energy is not a vector. It's never going to tell us about direction. Only momentum, which is a vector, can do that, right? Velocity is a vector. Momentum is a vector and will give us speed and direction. In other words, it will give us the velocity, right? So in that case, what's our only choice? Physics principle number 4, we would have to use the law of conservation of momentum. We could not use the law of conservation of energy, okay? So when in doubt, use conservation of momentum because it always works, right? And, I mean, bonus, it also gives us more information and gives more info, right? And the more info I'm talking about specifically is direction, right? So if we need direction for our question later on, maybe, right, it might be good to get it with momentum. Okay, so again, you're probably saying right now, why would I ever use conservation of energy? It doesn't seem much easier. It does get a little bit easier to use conservation of energy when we go two-dimensional with conservation of momentum in the next lesson. So in those cases, if it is an elastic collision and they do just ask us for the speed and not the velocity, like we don't need direction, in those cases, we can save ourselves a lot of work by using conservation of energy, though conservation of momentum will still work. All right. Okay, so here's an interesting one. Let's take a look. A ballistics pendulum is a device used in forensic science. A block of gel is hung from a fixed surface, then shot with a bullet. The bullet embeds in the gel, so you can see it's embedded there afterwards, in an inelastic collision. Okay, so that makes sense. We wouldn't really realistically expect that to be an elastic collision just because there's going to be heat and sound and, deforming of the gel, causing the pendulum to swing to some maximum height. The speed that the bullet was traveling can then be determined based on this height. Right? So that's pretty cool. Based on how high that goes, we can work out how fast the bullet was going and use that to analyze, forensic situations. Okay. So the speed that the bullet was traveling, I already said that, can be determined based on this height. So using the information given in the diagram, determine the speed of the bullet before impact. Okay, now, this is a bit of an interesting one when we think about it here, right? Because your first instinct is probably to say, okay, well, we can use conservation of momentum. That's good. That is a good instinct to have. But then you start thinking about it and you realize, but the final momentum in the system is actually like 0 here, right? Because this is a pendulum like we studied in Physics 20. This is going to swing up to its maximum height, right? And then it's going to stop, and then it'll, go back and go back and forth like this because it's a pendulum, okay? And so we can see here that like momentum doesn't seem to be conserved within the bullet gel system, right? Now, again, remember, I'm not lying when I say that momentum is always conserved. but it's possible that it has left our system here, right? Again, sometimes students will say to me, how can momentum be conserved? Like if I throw a ball at the wall doesn't move, right? But that just means our system, we're not defining it big enough, right? If we actually think about like the wall itself and the building, believe it or not, it did impart some little tiny amount of momentum to it. Okay, it's just that the building's mass is so large that you barely notice its velocity change, right? So momentum is always conserved, but sometimes the system is, large and it leaves our system, and so it can be hard to track it. So it's not that the law of conservation of momentum was violated here. It's just that we actually kind of need to think about an in-between stage. So this is a type of question that they pop up. You'll see some extra examples like this in the filled in notes. Okay, I won't go through them in this video, but where we actually kind of have to think about like before, middle, and our final conditions. Okay, because we know that the bullet came in, it hit the ballistics gel, right? And then the gel and the bullet together swung up to this position here, okay? But something happens in between those. Let's just think about the moment directly as it impacts. Okay, and so again, the reason I kind of want to think about this middle stage here, right? We kind of can see we can't rely on conservation of momentum to go from here to here. Again, not because it's not true, not because the conservation of momentum is being violated, but because it's not necessarily staying in our system, right? There's this external force largely caused by the tension in the two strings here as it, swings up, okay, that is changing the momentum of the system. It's an external force acting to change the momentum of our bullet block system. So if we expanded our definition of the system, we might be able to see momentum conserved, but how are we going to calculate the momentum lost to, the ever so slight transferring of momentum into the roof and the building and even the earth itself, right? That's kind of hard to do. Plus, we got multiple axes of motion. So it's not only moving to the right now, it's also moving up, again, due to the action of that external force. Okay, so while conservation of momentum is always true, it might not be that helpful for going from here to here. And that might make you say, okay, so can we use conservation of energy? Now, we are going to, actually, in a certain step, but we know that we can't use conservation of energy to go straight from here to here, right? We can't go straight from here to here. Do you see why we can't do that? Because the collision itself is inelastic, right? Now again, energy is conserved from here to here, but the fact that it's inelastic means that kinetic energy is not conserved. We don't have equations for the type of energy, right? I mean, you might say, okay, but we do have potential energy, right? But in an inelastic collision, that means that we are going to be losing energy as, stuff like heat and sound and deforming the ballistics gel, okay? And so that's why this kind of middle step here is key to think about, because let's just trace through here. We have the bullet before it impacts. This is the instant after it's already impacted. So the collision part has already happened. The heat has been released, the sound has, been given off, the kinetic energy that was going to be lost out of the system, the mechanical energy that was going to leave the system, has now left, and the bullet, what's left over, will become the kinetic energy as the pendulum bullet system starts to swing, right? So, was kinetic energy conserved from, or mechanical energy, I should say, conserved from here to here? Not quite, right? Because the collision has to happen. But once it's embedded, the collision's already happened. And now it starts to move. And that's the key here. So this is kind of a beginning, middle, end type one. So we can use, right? We can use physics principle number 5, that's the law of conservation of energy, to think about going from here, our very final conditions, to the moment just after impact, okay? Again, the bullet has already embedded here. Bullet has embedded. So some mechanical energy Remember, mechanical energy is the sum of kinetic and potential already lost as heat and sound, right? And that's what's going to allow us to set up a conservation of energy calculation, because now it's lost its heat, its sound, it's just kinetic energy of it. What does that kinetic energy get converted to? Gravitational potential energy, just like a pendulum we would have studied in physics 20, right? So once we now know the height that this has reached, right? So we can calculate its gravitational potential energy. We know that's just mass. We have the mass of the bullet and the mass of the gel times the acceleration due to gravity times the height that it got lifted to, right? So that's the gravitational potential energy it ended up with. So that must have come from the kinetic energy it had here, not the kinetic energy the bullet had here, because some of that is going to get lost as heat and sound. But once it's embedded, whatever kinetic energy this has is just going to become the gravitational potential energy it ends up with. So let's follow that thread, right? Whatever gravitational potential energy it ends up with here is the kinetic energy it had here, just in the instant after it embedded, okay? With that kinetic energy, we can find the speed that this thing started moving at, right? And we know we can't use conservation of energy to go from here to here, but we can use conservation of momentum to go from here to here, because it's an inelastic collision, meaning that kinetic energy was not conserved, but momentum is always conserved, right? And from the instant before impact to the instant after impact, this is an isolated enough system in terms of momentum that we can do that. So there's our game plan, okay? We can use physics principle number 4 to then go back to here, use conservation of momentum to then figure out, okay, what was the initial momentum of the bullet, and therefore find its momentum. So there's our game plan, okay? We're going to use conservation of energy to figure out how fast the bullet block system was moving in the moment after impact, okay? And then we can use conservation of momentum to figure out how fast the bullet was moving before the impact. We can't use conservation of energy here because kinetic energy is not conserved, right? Total energy was, but we don't have ways of calculating or keeping track of that heat and sound energy that left the system. So let's see if we can put this plan into motion here. All right, so first we were going to use conservation of energy to figure out how fast the system was moving here, right? Again, we know we couldn't use it from here to here because it's an inelastic collision. That's one of the things that made us say in the first place, okay, we got to think about the middle step here, right? Can't use conservation of momentum, can't use conservation of energy to jump straight from here to here. So that was a clue that, okay, this is not quite an isolated system. So let's think about the middle step here where we can approximate an isolated system between here and here and here and here, okay? So first up, let's use conservation of energy. I'm just going to give these, I'm going to call this like initial, I'll call this, let's just say M, maybe M will be confusing. Let's say D for during, and we'll say F for final. So initial, during, and final. Didn't want to use the M just because there's lots of M's already for masses and stuff. So let's use conservation of energy to figure out, to go from during to final, right? Or from final to during. So since the collision's already happened, that heat, sound energy has already been removed from the system, we can now say that the total energy mechanical during will be equal to the total mechanical energy final, right? And so, like always, right, like we would have done in physics 20, think about the types of energy we have here. Well, it's just going to be the kinetic energy of this system, right? The bullet came in, lost heat and sound energy, and whatever was left over as kinetic energy, this system now moves kinetic energy, right, until that kinetic energy is converted into gravitational potential energy, making it get higher. So for the during stage, we just have EK, right, kinetic energy. I'll say G for gel, so bullet gel system, is equal to, afterwards, it's just got gravitational potential energy, right? So EP, okay? And then if you go to your formula sheet, right, if you remind yourself of the equations you know and love from physics 20, right, for momentum and energy, we know kinetic energy is mv squared over 2, and gravitational potential energy is mass times acceleration due to gravity times height, okay? So, what kinetic energy do we have in the beginning? Well, we've got a mass. In this case, what mass is moving? It's the mass of the bullet and the gel, right? We have both of those, but that's the total mass that's moving. So we've got mass of the bullet and the gel times their speed during squared over 2 will be equal to their potential energy here, right? Energy can't be created or destroyed. It's already left the system, so it's a fairly reasonable approximation to say that all of that kinetic energy becomes all of this potential energy. We know how high it went above its starting position, so it's the mass of the bullet gel system times acceleration due to gravity times the height that they reach final. Okay, just saying that the total initial energy, or the total energy during, is going to equal the total energy afterwards, once it gets to that height. Okay, so just now having broken down, right, the mass of the bullet gel system is just the mass of the bullet plus the mass of the gel, now that they're stuck together like that. All right, so what do we know here? Well, they gave us the mass of the bullet, they gave us the mass of the gel in the diagram, right? So we got that there, we got that there. We know acceleration due to gravity. On Earth, it's 9.81. That's on the back of your formula sheet if you've forgotten, okay? And we know the height that it rose to. So the only thing we don't know here is the thing we want to know, right? How fast were they moving in the moment after impact, right? Because that, via conservation of energy, determines how high they could go. So let's go ahead and solve this equation for the velocity during squared, right? I mean, we could have called it initial. I just didn't want it to get confusing because we kind of have 3 stages here, right? But let's go ahead and solve for this. So we're going to multiply both sides by 2, and then we're going to need to divide both sides by their combined mass. And look at this. Something nice is going to happen here when we do that, and something we actually already knew, that mass doesn't make a difference here. We've seen that in physics 20, okay? They just cancel out, right? We're multiplying by their combined mass there, and then we're dividing by their combined mass. So it turns out that the speed during squared is just equal to 2 times acceleration due to gravity times that final height they reached. Last step to isolate here would be square root both sides, and we get that the speed of the system in the moment just after impact would be the square root of 2 times g is 9.81 meters per second squared times the final height they reached, which is 20.5 centimeters. Be careful, right? Reminder that the conversions are on the back of your formula sheet. A centimeter is 1/100th of a meter, right? Or there are 100 centimeters in 1 meter. So we're going to divide by 100 to get that this is 0.205 meters. Want to make sure we're in standard units. 0.205 meters. And I got that the speed of the system, just going to move up here, the speed of the system during, or like in that middle step there, right after impact, was 2.005517 meters per second. Okay, so just to recap, now using conservation of energy, we figured out that this must have been moving at, right, in the instant after the collision where the heat energy has already been lost, it had a speed of 2.005517 meters per second, right? And so now if we think about this, okay, we know we can't use conservation of energy to go from here to here because they told us it's an inelastic collision, right? But in an inelastic collision, momentum is still conserved, right? It's not until it starts swinging up like this and that external force transfers the momentum out of the system that momentum stops being conserved. From here to here, notice this looks exactly like every other question we've done, right? Now we're back to a simple, car rear ends a truck type question. It's just a bullet hitting a block of ballistics gel. So now we can use Physics principle number 4, conservation of momentum, to figure out how fast was this bullet moving, because we know how fast they move together afterwards and we know their mass. Therefore, we know their momentum here. So we can figure out the total momentum that must have been in the system here. So let's go ahead and do that now. All right, so trying to figure out what is the velocity of the bullet initial, right? Now that we know how fast they move together after the collision, we can just say, well, momentum is conserved even in inelastic collisions. So the total initial momentum will equal the total final momentum. Well, initially, we've just got the bullet, right? I mean, we could add this into our equation if we want, but the pendulum isn't moving initially, so its velocity and therefore its momentum is 0. So really, we just have the momentum of the bullet initial being equal to whatever momentum they have afterwards once embedded, and we've got one object there. So the momentum of the bullet gel system final, right? And P equals mv. So the mass of the bullet initial is the mass of the bullet times its initial velocity. We know its mass, we want to know its velocity, okay? And that will be equal to, well, the momentum of their combined mass, the momentum of their combined mass, which is just their combined mass bullet plus mass gel, times their combined velocity, which we just found in the first step, right? That's why we found it. So times the velocity of, I said final here, I guess I should say during, if I'm being consistent, okay? The velocity of the bullet gel system during, meaning during, again, just kind of to stand in for in between initial and final, okay? So now, we want to solve for this, the velocity of the bullet initial. So let's divide both sides by the mass of the bullet, and we get this equation, right? And we know all of this stuff. We know the mass of each object. We know the velocity that it has in the moment after impact. So we can calculate here for the velocity the bullet must have had before impact. So plugging in our numbers here, the mass of the bullet, be very careful, 24 grams, right? But we want kilograms. There are 1,000 grams in 1 kilogram, so dividing by 1,000, we get 0.024 kilograms. That's the mass of the bullet, plus the mass of the gel, which is 3.25 kilograms according to the diagram. So plus 3.25 kilograms times their combined velocity. Well, we figured that out in the last question that it's not the last question, the last step, that in the moments after impact, they must have been moving with this speed in order to reach that height, following the law of conservation of energy. And now we want to divide that by the mass of the bullet. And the mass of the bullet is 0.024 kilograms. So calculating that all out, I got that the initial velocity of the bullet must have been 273.5859 meters per second, or how many sig digs? 3 here, 3 here, 3 here, 3 in the 9.81 we used. So okay, we get 3 significant digits. So that is 274 meters per second, okay? Can't say much about direction, but they didn't actually ask us for velocity anyway. They asked us for speed, so we don't need to state a direction here. The speed of the bullet must have been 274 meters per second, okay? So again, it's a little bit of a thinker at first, right? But it comes down to the fact that you realize, like if you think about this, you realize, oh, conservation of momentum doesn't quite work to go straight from here to here, right? Nor does conservation of energy. Again, not because they're not true, but going from here to here, we don't have an isolated system, right? And so that's a clue to think, okay, is there something in between we can make use of, right? It might not be an isolated system all the way from here to here, but in terms of energy, we can approximate a isolated system from here to here because the mechanical energy has already left in the form of heat and sound in the moment after impact, right? And then from here to here, we can definitely approximate it as an isolated system in terms of momentum because that external force acting to, change the direction of its momentum and impart some of the momentum, well, that hasn't come into play yet. It's just the instant right after momentum. So, or right after impact, sorry. So whenever you find yourself saying for these types of problems, if you're like, oh, I don't know, ask yourself, is there maybe something in between? Right? Is there maybe something in between that could be used, a middle stage where we could possibly, often it involves using conservation of energy or sometimes your kinematics equations to figure out what happened just after impact, before the effects of it being a non-isolated system took hold, or just after. Okay? Couple examples from diplomas here, and then we are done. So I often find it helpful when they give you this information in these diagrams. It's often nice to actually read the question first, because then you kind of know what the important information that you really want to be paying attention for is. So it says, for the time interval when the two carts are in contact, match the directions and relative sizes as numbered above with the descriptions given below. So direction of the force of cart 2 on cart 1, direction of the impulse of cart 1, magnitude of the impulse of cart 1 compared to cart 2. Okay, so for these direction ones, we're going to be talking about which direction the force and the impulse on cart 1 is, okay? And then for this one here, we're going to use, is it twice as large, same size, or half as large for how the magnitude of the impulse of cart 1 compares to the impulse of cart 2. Okay, so now we know what we're kind of thinking about. Let's go ahead and jump in and read this one. So two carts traveling at the same initial speed, okay, move toward each other on a table as shown below. Car 1 has a total mass of 500 grams. Cart 2 has a total mass of 250 grams. All right, so nothing too surprising here, right? Kind of like our simulation we were using earlier. A cart with twice the mass is moving towards a cart with, well, half as much mass as it. They're moving towards each other with the same initial speed. The carts collide. After contact, the carts remain separate from each other and move independently. Okay, so they don't stick together. All right, so let's just take a look. Which direction of the force of cart 2 on cart 1, which direction will that be in? Well, okay, when cart 2 and cart 1 collide, right, if we picture that, they're colliding, they're in contact with each other. Cart 1 was moving to the right. When it comes into contact with cart 2, it's going to push it like this, right? Newton's third law says equal and opposite. So cart 2 is going to push on cart 1 like that, to the left, right? We can kind of see, yeah, while they're in contact with each other, cart 2 is going to push cart 1 to the left, while cart 1 pushes cart 2 to the right. So which number direction matches that? Cart 2 on cart 1, right? Cart 2 will be pushing cart 1 to the left, so that looks like option 4. So next it asks us for the impulse of cart 1. What direction is the impulse of cart 1? Well, I mean, a couple ways we can think about this, and they all are going to bring us to the same answer, right? Cart 2, we just said, is pushing cart 1 to the left. Well, if you're pushed to the left, which way is your momentum going to change? To the left, right? I mean, another way to think about it, cart 1 is coming in, it's going to be moving to the right. We know cart 2 is going to, like, hit it, and at the very least slow it down, if not actually cause it to rebound. But either way, that's a leftward impulse, right? We're taking away some of its rightward momentum. So how will cart 1's momentum change if it's pushed to the left? Its momentum will also change to the left, right? It might not actually end up moving to the left, but its impulse will be to the left either the way, whether that means it's now going to the right and a bit slower, or if it actually was big enough impulse to actually change its direction of travel altogether. Either way, that's an impulse to the left. Now this is the one that students actually, most of them missed this, maybe not most, but this was a question that was flagged as students didn't do very well on this on the diploma. And for most students who got it wrong, they got it wrong because of this. So the magnitude of the impulse of cart 1 compared to cart 2. Now, a lot of students said that cart 1 would either have half as large of an impulse or twice as large of an impulse. And we can guess that they're getting that from the fact that the cart has twice the mass as cart 2, right? But remember, this is the law of conservation of momentum. if one object's momentum changes, the other one's has to change the same way, but in the opposite direction for total momentum to be conserved, right? I think what students were probably thinking is that because this one has a larger mass, its velocity won't change as much, right? But there's no law of conservation of velocity. There's a law of conservation of momentum. So they're right. The velocity won't change as much for this one, but the momentum change will be equal and opposite, as we talked about in all these previous examples up here, right? So the impulse will be the same size, opposite direction, but same size for cart 1 compared to cart 2. Right? Their impulses must end up canceling each other out. So the answer we would bubble in here would be 4, 4, 2. And that's the correct answer. 4, 4, 2. 4, 4, 2. We don't need the last box, so we leave it blank. Whenever we don't need all 4 boxes, you always still start in the first box. If you don't need any when you're done, great. Okay? But always start left and leave the last ones blank if they're not needed. Right, it's the same logic we've been applying this whole time. The forces are equal and opposite while they're in contact, and they're in contact for the same amount of time. So if a change in momentum, an impulse is a force times a time, and they're experiencing the same magnitude force for the same amount of time, they have to experience the same impulse. Okay, so last example for today, another one from an old diploma. Looks like it's going to have to do with graphical analysis. Again, kind of nice to just read the question first so we kind of know what we're doing, and then we can go back and sort through the information a little bit more accurately. So based on a point on the line of best fit, okay, so we need a line of best fit. Notice they actually haven't given us it here, so we'll have to draw our own line of best fit. I'll review what we want from a line of best fit in just a moment here, okay? But if cart 1 had a speed of 6 centimeters per second before the collision, then the combined speed of the 2 carts after the collision would be a.b centimeters per second. You'll need to record the values of A and B. Oh, this is a two-parter. So then based on the slope of the line of best fit, the combined mass of the 2 carts is E.F kilograms. Well, that's nice. They're telling us we want the slope. They don't have to tell us that. We can use the equation to tell us that we need the slope, but that was nice of them. You will need to record the values of E and F. The next page is blank for you to do work on. Okay, so the values of A, B, E, and F. So we're looking for their speed once combined, and then we're also going to be using graphical analysis to find the combined mass of 2 carts. So sounds like we're talking about 2 carts colliding. Sounds like a good conservation of momentum situation. So let's just read here. Students perform an experiment using 2 low-friction laboratory carts. So low friction telling us it's close enough to an isolated system. There's not enough friction to like noticeably change the total momentum in the system. All right. A piece of timer tape is attached to cart 1. Timer tape is tape that, it essentially allows you to record how fast something was moving. When I teach physics in person, we use this all the time. I do a lab very similar to this, actually. In fact, pretty much the same lab. Unfortunately, in online, I can't assume that you have one of these sitting in your house, so I can't make you do it. But it's a spark timer, so what it does is it just goes tick, 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 and it marks the tape. And the tape you can see is attached to the cart. So as the cart moves and this marks the tape, what you can do after is measure how far apart the ticks are, and you know the time between each tick. So if you know how much time went by between the 2 ticks and you can figure out the distance between them, then V equals D over T. So you can figure out the speed of the cart. Okay, anyway, the timer makes a mark on the tape each 0.1 seconds. So there you go. If you measure how far apart the ticks are, you can figure out that it went that far in 0.1 seconds and therefore figure out its speed. All right, so cart 1 is pushed towards cart 2, which is initially at rest. Okay, so cart 2 is initially at rest. The carts collide, the piece of clay is deformed and holds the carts together as they continue to move. So this is what we call a hit and stick collision, right? They hit, they stick together, and then they move as one object. The mass of cart 1 is 1.54 kilograms. Okay, so this is 1.54 kilograms. The students repeat the above procedure manipulating the initial speed of cart 1. So they push cart 1 with a bunch of different speeds, they let this experiment happen, and then they make a graph. So whenever given a graph, always look at what you're dealing with, right? You want to make sure you know what's on your y-axis and what's on your x-axis. On our y-axis is the speed of carts 1 and 2 as a function of the speed of cart 1 before the collision. So we've got on our y-axis the speed of carts 1 and 2 after the collision, so how fast they were moving together afterwards. And on our x-axis, it's the speed of cart 1 before the collision. So that makes sense, right? Because this, how fast they're moving afterwards, just depends on how fast we pushed cart 1 before, thanks to the law of conservation of momentum. If we push cart 1 faster, we give it more initial momentum, and therefore afterwards there will be more initial momentum, and therefore carts 1 and 2 would be moving together faster afterwards, right? So that's what we always do. We put the dependent or the responding variable on the y-axis and the manipulated or the independent variable on the x-axis. This depends on this. Okay, now, before we do any kind of graphical analysis, we need a line of best fit, right? Because graphical analysis is all about slopes, areas, intercepts, and sometimes just reading values off of the graph, right? We can't do any of that until we have a line of best fit. We cannot use these data points. Remember, right? Data is not perfect, okay? This one we can see is a little bit lower probably than it actually was, but for some experimental error, our measurements are a bit off, right? Some of these are probably a little bit higher than the true value. Some of them are a little bit lower than the true value. We cannot use individual data points. Otherwise, why did we do the experiment all of these times, right? We could have just done it twice. Like if I do a slope by going run, rise, am I using any of this data that we worked so hard to collect? Right? Is my answer going to be as accurate as it could be? Not at all. So what we do is we draw a line of best fit, sometimes called a trend line, because the trend line uses all of the data. It gives us the trend, the overall trend of how y actually depends on x. It takes all the little quirks of all our individual data points and it kind of smooths them all out to give us the overall trend in the data. So let's remind ourselves of what we need to do when drawing a good line of best fit and what not to do. Okay, so the number one thing, and really this is the whole idea here, is we need one straight line that needs to represent the trend in the data, right? We need one straight line, A, because that averages out all our data and gives us the overall trend, but B, because we need one straight line to be able to calculate the slope of it, right? A common student mistake, this is more common in physics 20, by physics 30, most students have stopped doing this, but a common one is to just connect the dots, right? Do you see why that's no good? What have we changed? What's the slope of this line if we need the slope? What's the area underneath this if we need the area, right? So we definitely do not just connect the dots, right? This doesn't tell me anything about how y depends on x, right? It's all different in different places. I can't get an idea of how y depends on x from this line because it's not a line, it's multiple different lines. Is it really true that y depends on x in a different way when x is these numbers versus when x is these numbers? That's what we're suggesting with something like this. So we don't want to do that, okay? That is not good. We want, more than anything, okay, the first step with this is step back, look at the data points, okay, and try this now. Just visualize the line that is suggested by this data, right? We can see that, okay, as x is increasing, it looks like y is increasing as well, right? And can you kind of visualize the line that represents this trend, right? So something like, this isn't going to be perfect, I'm just doing it freehand, okay? But we want it to represent the trend in the data. So maybe something like that, okay? Probably could have done better, but it's pretty solid, right? Maybe I could actually have shifted it up a little bit just because there's 3 points up there. Now I've got 3 points above, 3 points below. That looks pretty good. But do you see what I mean, right? That line is just representing the trend that our data suggests, right? Okay, that is the number one goal. First things first, that is what we're trying to do. Draw the line that represents what the data is suggesting in terms of how y depends on x. Now there's a couple kind of checks we can use, but again, this is really what we're doing. These are just kind of tools we can use to check if we've done a good job or not, right? One of the checks we use is that there should be roughly as many points above the line as there are below the line, right? Now we got to be careful because sometimes students get obsessed with that and they'll say to me, okay, I drew my line of best fit, right? And they'll say, it's good because there's 3 points above the line and there's 3 points below the line. Well, true, but does this line look like what the data was suggesting, right? It's way off, right? It says that as x increases, y is decreasing, but that's not what our actual data points from our experiment suggested at all, right? So we don't want to do that. It's not the be-all, end-all. Sometimes students get a little too obsessed with this one and they forget the big idea. We want it to represent the trend in the data. Another big common student mistake with lines of best fit is trying to force it through certain points. Students really feel sometimes like every line of best fit should go through the origin. They feel like it needs to go through 0, 0. There's a lot of situations where when x is 0, y isn't 0. In fact, looking at this data here, right, does it look like it should be headed to the origin? If we try to force our line of best fit through the origin, okay, even if I try to do the best I can with it, it's not great, is it? Right? Like compare that red one to that green one there, right? This is what happens when I force it through a point that I think it should go through, right? But there's no reason that data did not suggest that it was projected back to the origin here, right? Compare how this represents the trend in the data to this one. Doesn't this look a lot closer, right? This looks a lot more close to what our data points individually were suggesting. Okay, one kind of way we can think about it, I like this as a way to basically check your work, right? Have you minimized the average distance of a data point from the line? Meaning like overall, have you made it so that the points are as overall on average as close to the line as they could be, right? One way to think about it is that if you were to take a red pen and you were just to connect every point to your line, have you kind of minimized the amount of ink you would have to use, right? We did an okay job with the green one there, right? Like this though, oh boy, most of my points are actually really far away from my line, right? This one, you can see now, oh yeah, look. These data points are really not being super well represented by that line of best fit, okay? So you must use a ruler, right? Don't even think about not using a ruler. More than anything, you're trying to represent the trend in the data. So step back, look at the data points, visualize the line that represents that trend. Okay, and my tip too, always do it softly in pencil at first. I've been doing lines of best fits for a long time, right? I'm a physics teacher. Even I often don't get it on the first try. I'll draw in my line of best fit, I'll step back and look at it and I'll realize, it's a little bit off. It needs to be shifted a bit this way or that way. Honestly, it's pretty rare to nail it on the first try. So draw it lightly on your first go, and that way you can easily erase if you need to, because I'll be honest, you probably will need to once or twice, right, until you get it to where you're happy with it. But with that in mind, with those kind of principles in mind, let's see if we can draw a line of best fit for this so that we can actually start doing some graphical analysis, okay? So step back, visualize the line here, okay? Visualize the line suggested by this data, and then we'll pull out our rulers. I'll pull out my ruler, and I'm going to try to draw the line that represents what these data points should suggest. All right, so here's what I came up with after pulling out my ruler and trying to draw the trend line, the line of best fit, okay? It took me a couple tries, even just now, I'll be honest, right? So don't feel bad if you're not like perfectly happy with it on the first try. It can take a couple to get it to where you think it looks about right, okay? Even this, honestly, I could use a little improvement maybe, but I think it's close enough to be reasonable, and I don't see any glaring issues with it. So we can go through our checks here, right? I've got 2 points below, and I've got, 2 points above, a couple that are right on the line. I think it looks pretty reasonable. Notice I did not force it through 0, 0 because that data definitely did not suggest that it was headed to 0, 0, right? If I were to try and force it through 0, 0, that doesn't look very good, right? Like that does not look like it represents that data very well. So this is one where, yeah, there's no reason for it to go through the origin there, okay? And so taking a look here, okay, we've got, yes, this one's a little more above than the other two are below. Oh boy, I don't know why it keeps jumping up to the top of the notes there. Sorry about that. Right? Yes, this one here is a little more above than these are below, but it kind of balances out because, first of all, it almost looks like that one up there might even be like an erroneous data point, meaning that it was something went wrong on that trial. It's quite off the trend suggested by the others. And plus, we've got 2 below here. Yes, 2 above, but this one's only a little bit above, so I think that kind of balances out here. I would say I'm feeling pretty good about this line of best fit. More than anything, when I look at that, I feel like it does represent the trend in the data. Okay, so I'm feeling okay with that line of best fit. Now, what are we going to have to actually do to answer this question? So based on a point on the line of best fit, if cart 1 had a speed of 6 centimeters per second before the collision, then the combined speed of the 2 carts after the collision would be A point B centimeters per second. We need to record the values of A and B. So this is the great thing about graphing our data, right? It allows us, again, no individual trial of an experiment is ever going to be perfect. Things are going to go wrong, right? But the more trials we do, the better picture we get of the trend in how this variable actually depends on this variable, right? If we just did one trial, how do we know that that data is any good, right? If we messed it up, we don't really have a way of knowing, right? But if we do many, many, many trials and we see that most of them fit kind of along a certain trend, then we can be more confident in any data that fits that trend, right? And we can also be more confident in saying, ooh, we might have messed something up on this trial, right? It's quite above what the other trend does. Same actually applies to the one we're looking for, right? We want to know if we were to repeat this experiment, right, and give it a speed of 6 centimeters per second initially, what would we expect the speed to be after the collision of the 2 carts together, right? Well, we can actually see here, like this data point, they did that. They did 6 centimeters per second. It doesn't actually look that great, does it? Right? It looks like this one might have been a little bit off. It doesn't fit the trend suggested by the other data as well as it could, right? So instead of just trusting that data point, let's trust the line of best fit, which kind of is a way of averaging out all of the data and trying to incorporate all of it into determining what is the relationship between this variable and this variable. So for this, we actually just need to read off the graph. So remember, once you draw your line of best fit, you forget that these points exist, right? If we just now use this point, there was no point in doing all the other experiments because we're not using any of them. We're just using that data. With the time we gave the initial cart 6 centimeters per second, and we saw that it ended up with a final velocity of 2.4 centimeters per second, right? What was the point of doing all the other ones? What was the point of graphing it and drawing our line of best fit if we were just going to use that one set of data, okay? So using the line of best fit, forgetting about the, other one there, okay, or the single data point, let's just read it off. So if we gave it 6 centimeters per second initially, the data, the trend, and the relationship in the data suggests that the carts should end up with, looks like it's right in the middle of 2 and 3 at 2.5 centimeters per second. That's the most likely outcome based on our other data now, right? So A point B centimeters per second is 2.5 centimeters per second based on our line of best fit. So what's A point B, or what are A and B? Well, if A point B is 2.5, A is 2, B is 5. Okay, now The diploma is reasonable here because they know slight differences in your lines of best fit might lead to slightly different answers, okay? So the diploma marked any points and answers consistent with a reasonable line of best fit as correct. So some possible correct answers include, they're actually not limited to this. I think they actually took up to 2.6 even, but you can see so far we're good. So far, right? 2.5 was an acceptable A-B. They also took 2.4, and I think, if I remember correctly, they took 2.6. So don't panic too much about your line of best fit. Like if you're like, oh my goodness, if I'm off by just a tiny amount, I'll get the wrong answer. No, not quite. They are reasonable about it, okay? But if you have to draw the line of best fit, right, they want it to be reasonable. Like whatever that line would give us, that would not give us the correct answer because that's nowhere near matching the trend in the data, okay? All right, so we answered part 1. Now part 2, which refers to the slope. So it says, based on the slope of the line of best fit, the combined mass of the two carts is E.F kilograms. Okay, so what does the slope have to do with this? Remember, we're not like guessing here. The equation will tell us. So what is the equation that has to do with this situation? Well, it's just a conservation of momentum situation, right? We have cart 1 has an initial velocity and therefore an initial momentum. It collides with cart 2 and they move together with the same momentum, right? And therefore a different velocity because since the mass went up, the velocity is going to have to decrease. And then we plotted that new velocity as a function of the velocity we gave cart 1 in the first place. So how do we start getting an equation here so we can think about what does the slope have to do with it? Well, let's start basic like I always say we should, right? The total momentum initial will equal the total momentum final, okay? Now initially, we just pushed the first cart. I'm just gonna include both carts here so we can think about it. We got two objects. We've got cart 1 and we've got cart 2, right? Their total initial momentum will equal their total final momentum, except final, they are stuck together. So I'll say 1, 2, final, right? Because they're stuck together as one object afterwards. So there's just the one momentum to think about, okay? Now, cart 2 was initially at rest, don't forget. So momentum 2 initial, that makes things nice. That's just 0, right? This is just 0. So unsurprisingly, it's what we just said. The initial momentum in cart 1 will be the same as their final momentum when they're stuck together and moving, okay? So what is momentum of cart 1 initial? Well, it's cart 1's mass times its initial velocity. And that's going to be equal to, okay, what's momentum 1, 2 final? Well, the mass of that object, quote unquote object, is just the two objects stuck together. So its mass is mass 1 plus mass 2, which, hey, you can see this is getting good, right? Because that's what we're looking for. We're trying to figure out the combined mass of the two carts. That's mass 1 plus mass 2. That's what we're trying to figure out. Now, that mass times their combined velocity is their momentum. And that's the final momentum in the system. Okay, so like always with graphical analysis, right? Take what you're looking for, solve for it, and then let the equation tell you what to do, right? With the graph. If it tells you to divide y by x, you're looking for the slope. It tells you to multiply y by x, you're looking for the area, right? So keep in mind, what is on our y-axis? It's the speeds of carts 1 and 2 after the collision. So that is v1, 2, final. That's on our y-axis. Before the collision, it is the speed of cart 1 before. So that's v1 initial. That's on our x-axis. Well, look, those have both showed up in our equation, right? There's our x-axis variable. Here is our y-axis variable. So this is looking good. This is looking like we can, rearrange this to figure out what we need to do with the slope to actually calculate that mass 1 plus mass 2 that we're looking for. So I'm just going to isolate it. I'm going to divide both sides by v1, 2 final. And now that we've isolated for what we want, right, same as always, look at the equation. What is it telling us to do with the variables from our graph? So this velocity of cart 1 initial, That is on our x-axis. So this is x, okay? And then their combined velocity after the collision, that is on our y-axis. So it's telling us to actually divide x by y. So be careful there. Is that the slope? That's actually 1 over the slope, right? That's the inverse. That's rise over run. So it has to do with the slope, but it's not as simple as just mass times the slope here. It's actually mass times 1 over the slope, right? It's mass 1, the mass of cart 1, times our run over our rise, right? Now that's still using the slope. We're still going to find the slope, but we're going to do 1 over it, right? Or we're still going to find rise and run, but we'll actually be dividing run by rise instead of rise by run. Do you see that, right? This is x and this is y, our x variable and our y variable. Okay, but it doesn't change anything. We're still finding the run, we're still finding the rise, and we're just flipping the order we divide them, okay? So what we're doing here, run over rise, that's 1 over the slope, right? That's the inverse of the slope. So this is mass 1 divided by the slope, if you like, or times 1 over our slope, okay? So all we've got to do then, we know mass 1, it's 1.54 kilograms, right? If we can find the slope of the line our best fit and then divide 1.54 by it, we can see now that we'll have their combined mass. So we're back in Math 10, we're finding the slope of a line. Now, when finding the slope of a line like this, right, don't make your life harder than it has to be if you can avoid it. What we want to look for are nice, easy to read points. And I mean by that, points where we don't have to estimate, right? Like I wouldn't really want to use this point here because like, where is that? Is it at like 1.83 or like 1.84? It's a little tough to say, right? It's much easier if we can find points that are directly on the intersection of some grid lines. Like, look at that one. That one jumps out to me. That's a very good point, right? I don't have to estimate. I know that it's here on the x-axis and it's here on the y-axis. So let's use that as one of our points, definitely. Okay, that's a good one. Let's look for another one here. How about, actually, maybe up here? That's pretty good. That looks like it's just about right on that intersection. So I'm going to use those 2 points on the best fit line. Again, I am not going to use the data points. Otherwise, I'm not using all of my data. I'm just using those 2 trials, right? What was the point of doing the whole experiment then? Okay, so now we just need to get the rise and the run for those 2 points. So let's do run. So to go horizontally from this point to this point, I have to run that far. Looks like that is from okay, it's going up by 0.2s here, so 3.246. So from 3.6 to 6.2, right? So to figure out how much that changed by, you know, where we ended up minus where we started. 6.2 centimeters per second minus 3.6 centimeters per second. Again, that's just from reading off here and here. That's how much we ran, okay? Which gives us a run of 2.6 centimeters per second, okay? So now do the same for the rise. To rise from this point to this point, okay, showing our little rise-run triangle here. To rise from that point to that point. Pick those 2 because they were easy to read. Looks like we ended up at, now be careful, our y-axis is scaled by 0.1s, not 0.2s. So this would be 2.6, okay? So our rise is going to be 2.6 centimeters per second minus where we started there. Looks like 1.4 centimeters per second. So that's going to give us a rise of 1.2 centimeters per second. All right, we've got our rise, we've got our run. We already let the equation tell us what to do with them, right? So here we go. We're about to do it via graphical analysis. So their combined mass, mass 1 plus mass 2, we said was going to be equal to mass 1 times run over rise, okay? So times run over rise. And now we know that our run is 2.6 centimeters per second, and our rise is 1.2 centimeters per second. And we know that the mass of carp 1 is 1.54 kilograms, right? So putting this in and calculating it out, I'm getting that the combined mass using graphical analysis is 3.3367 kilograms, okay? Good sign here too that we had centimeters per second divided by centimeters per second, so those just end up canceling out. If you're saying, why didn't we convert those to meters per second? You're right, we totally could have. However, looking here, we could kind of see that they were actually going to cancel out. We would have got the same result if we had converted them both to meters per second, so we were safe in this case, okay? So they said record it as E point F, right? 2 significant digits. So E, rounding this correctly, our E point F would be 3.3 kilograms. So this is 3. And so you can see, hey, that went okay. We got one of the answers that was considered acceptable. Again, if you tried this on your own and you were off a little, like if you got a 2.6, I do believe that was actually accepted. I just put some of the reasonable answers that were accepted here. Okay, so 2533 would be our final answer, right? Now, again, I know that seems a little maybe intimidating at first, but notice, right? All I did there, I'll be honest with you, like I'm a physics teacher. When I first did this question, I did not know that we were going to get to this point, right? I had no idea how the slope was actually going to be involved. But I started here. I said, I know the total initial will equal the total final. That's going to let me write an equation, and then I can let that equation tell me what to do with the y variable, which is their combined velocity afterwards, and the x variable, which is their initial velocity before, right? So going through that, manipulating the equation to solve for what I wanted, okay, and then letting it tell me what to do with y and x. In this case, dividing x by y. So I actually wanted run over rise in this case, or 1 over the slope. All right, folks, and that wraps up lesson 2 of chapter 9. In the next lesson, we're going to continue to talk about conservation of momentum, but we'll look at it now in 2 dimensions. So far, everything has been in 1 dimension. They maybe crash left and right, but never like left and up or down and right. That's what we'll look at in the next lesson, but it's all the same principles. Okay, so go ahead. If you didn't do any practice questions before when we took that little pause, you can finish up those now. Make sure you're reaching out with any you're having questions about, anything you're stuck on or want to talk through. I'm always happy to help. Send an email and or book a meeting. I'm always in a good mood to go over physics. Okay, so there we go.